Thanks to the organizing committee for inviting us. And so we've divided this lecture into 4 parts. And in the first part of it, I'm going to focus on measurement in the age of AI, discovery, definition, and observation. And so our starting point for this entire lecture series is that AI is transforming a lot of things, but in particular for our purposes today, it's transforming measurement. So AI systems can convert high-dimensional, unstructured data, by which I mean data like text or images, audio, video, into low-dimensional variables that we can interpret and that we can use in statistical analyses. We wouldn't plug a book directly into our regression, but we might measure something about that book, with the language model and then be able to analyze that. This can often be done cheaply and at a massive scale. And so understanding the implications of AI for empirical analysis requires first examining how AI reshapes the measurement process. And I'm going to start by asking maybe what seems like a silly, very simple question, which is just what is measurement? Because I've found in working on these topics and discussing them with people that oftentimes are kind of differences in understanding and in evaluating the challenges raised by AI is a difference in understanding what measurement objectives are. And so I want to start by answering this kind of very basic question. In the context of social science, what is measurement? And so the core idea is that measurement is essentially representation. It maps a complex high-dimensional reality into lower-dimensional variables, lower-dimensional measures that we can then understand and analyze. And so it's inherently going to preserve some features of reality, but discard or transform many other features. And so oftentimes in our daily life, we might think of measurement as kind of a passive observation, how many degrees are on the thermometer, how many cups are in the measuring cup. But when it comes to social science research, measurement is really not passive, it's a disciplined simplification of reality. And so why is simplification necessary? Well, reality is vastly high-dimensional. We see this across, literary, philosophical, religious traditions. So Shakespeare said, there are more things in heaven and earth than are dreamt of in your philosophy. From Borges, we have to think is to forget differences, generalize, make abstractions. And measurement formalizes this simplification. It specifies what features of reality are preserved in the variables that we analyze. And so some of you may have heard the expression, the map is not the territory. In particular, Borges imagines cartographers who pursue perfect representation until they produce a map whose size was that of the empire. But this perfect map is actually useless because it no longer reduces complexity, it ceases to function as a map. And so this selectivity, it doesn't make measurement merely subjective, but rather the relevant question is, does a given simplification preserve the features needed to support useful inference about the underlying high-dimensional world for whatever your research question is? So we think of measurement, in short, as a disciplined, fallible, and purpose-oriented attempt to learn from reality through simplified representations. Mathematically, we can think of measurement as a projection that maps this high-dimensional reality into lower-dimensional representations that we're going to interpret and that we're going to analyze. And because X is high-dimensional, inherently there are many, many ways to map a given concept to a low-dimensional measure, and naturally these may preserve different features of reality, and thus they may support different empirical conclusions. And so in particular, I find it helpful to think about the different stages of measurement, and these lectures are going to be organized around the different stages of measurement and the implications that using AI for each stage has for downstream estimation. And so first of all, we have discovery. Given the complexity of the world, what features exist and are worth measuring? Then we have construct definition. How should the relevant concept be operationally defined? And then finally, we have observation. How can that definition be implemented at scale? And each stage of this measurement process involves different types of uncertainty, and they have traditionally been examined through different disciplinary and methodological lenses. So let me elaborate a little bit. Okay, so stage one, discovery, involves uncertainty around which patterns, dimensions, or relationships exist and are worth measuring. Methodologically, we would typically pursue discovery through theory or contextual knowledge. We might do exploratory analyses, but increasingly, unsupervised learning and data-driven discovery are being used to drive discovery. Okay. In stage two, construct definition, the uncertainty is about how a phenomenon that's of interest can be translated into some operational construct for a given research setting. So maybe you're interested in studying economic policy uncertainty and you have newspaper articles. How do you actually operationalize that so that you can measure economic policy uncertainty from the news articles? And again, oftentimes we come from theory, we come from domain expertise, maybe from piloting and even qualitative validation. Oftentimes we make do with whatever externally available proxies are available. Maybe expropriation risk for foreigners wouldn't be the perfect way to measure property rights, but it was the available way, and so kind of we do as best as we can with what exists. The formal literatures on construct definition are mostly in psychometrics and to a lesser extent survey design. And then finally there's observation. How accurately can the construct be observed at scale, and how do errors propagate to the target parameters? And so this is where statistics econometrics is quite well developed, and we look at this question through the lens of measurement error and semi-parametric inference with missing data. Okay. A final point that I want to emphasize about measurement is that traditionally we've treated it as fixed, typically. Measurement costs oftentimes prevent researchers from comparing different measurement functions. And therefore, we've often relied on externally constructed measures as fixed proxies for things that are theoretically meaningful. And so naturally the focus is on justifying the proxy rather than on comparing alternative measurement functions. However, AI as a measurement tool is changing this, and quite rapidly. And so we can think of deep neural networks as flexible implementations of measurement functions that learn structured representations from high-dimensional inputs, such as text, image, audios, and video. And these representations can then be interpreted and used in statistical analysis. And this is changing the measurement landscape by making it much more feasible to use unstructured data to construct variables for our analyses. So we can measure things that we could have never measured before, or maybe we could have measured them, but now we can measure them on a much larger scale. And so before neural networks, researchers often extracted low-dimensional features from unstructured data using hand-engineered rules. Neural networks take a different approach. Instead, they learn representations from empirical examples. And so essentially, they use millions to billions of learned parameters to transform the inputs, which are things like text or pixel data, which are inherently high-dimensional, into lower dimensional representations. Examples would be, you might transform it into a continuous vector, or you might transform it into a predicted label. I have a newspaper article. Does this newspaper article mention economic policy uncertainty? Yes or no? And so the input is the article text, and the output is that yes, no label. That's a low dimensional representation that's easy to include in regression analysis. And so neural networks are trained to perform specific tasks. They predict the next word in a sequence. In the case of a language model, they might classify an image. In the case of a vision model, identify objects, match text to labels, etc. And their parameters are adjusted through gradient descent. And so the key idea behind neural networks is that if you have sufficient training data and an appropriate objective, you can learn which features of the high-dimensional data that you need to preserve to perform that given task. Why are neural networks so powerful as measurement tools? Well, first of all, they generalize beyond the task which they were trained on. Language models are very useful for predicting the next word, but they can also perform a variety of other tasks. You might need to tune them on some additional data, but much, much less data than you would need if you were training it from scratch. And so you can take a general purpose language model, trained to predict the next word, and use it for all kinds of different tasks. Across many tasks, neural networks outperform human engineered rules. And then finally, neural networks are highly scalable. And so that means that we can substantially lower the cost of converting unstructured information into low-dimensional variables. I do want to caveat here, I don't want to sound overly optimistic. In many scenarios, credible AI measurement still requires substantial fixed investments. This is true for a lot of the work that I do with historical documents. If you want to achieve sufficiently accurate predictions, you may need to develop high-quality training data and then fine-tune a customized model. And so I don't want to imply that researchers, as a requirement, need to be comparing many different potential measures if it remains very costly to use AI to construct the measurement function, that can then be applied at scale to a particular measure. However, there are other settings where off-the-shelf or very lightly adapted models perform quite well. And this makes it inexpensive to construct many candidate measures of the same broad concept. And so in this setting, the bottleneck shifts from developing any type of scalable measure to choosing amongst many plausible measures, and these measures may yield different estimates of the target parameter. And so this, in my view, closely parallels the empirical revolution that came with dramatic declines in the cost of personal computing during the 1990s. And so cheap computation enabled researchers to estimate not just one empirical specification, but hundreds, thousands, or even millions. The I just ran 2 million regressions problem. And this forced the field to ask, what should discipline the choice amongst possible specifications, and what makes a specification credible? And in response to cheap computations, large literatures developed around topics like causal inference, robustness, multiple testing, et cetera. And so AI-enabled measurement raises an analogous problem. By expanding the set of feasible measurement functions, it underscores the importance of assessing what makes a measurement credible and how do we choose amongst multiple measurements. When measurement is costly, we might just inherit a proxy, adopt an existing definition, implement the only scalable procedure available. With AI, we can expand measurement possibilities at each stage of the pipeline. So in discovery, we can identify patterns or dimensions that the researcher doesn't have to specify in advance. With construct definition, we can generate and compare alternative operationalizations, and with observations, we can implement a chosen definition at scale. And so I want to elaborate on how AI is influencing each of the stages of measurement. Discovery, traditionally guided by theory, contextual knowledge, incremental advances in the existing literature, and this works quite well when the problem is sufficiently understood for pre-specified measurement to be well motivated. But the risk is if these are the only tools that we have available, we risk looking for the keys under the lamppost. That is to say, we only search for concepts that we already know how to specify. With data-driven discovery, the researcher specifies a representational procedure rather than a predefined construct. And so they don't say, I want to study economic policy uncertainty because this theory says it's important. Instead, they start with a procedure that allows them to discover, what topics do these open-ended survey questions focus on? And so examples of methods might include embeddings, clustering algorithms, dictionary learning methods, autoencoders. I know I haven't defined any of this, and Ashesh will be talking more about discovery after this lecture. But in short, these procedures summarize high-dimensional data by identifying structure that you, the researcher, do not have to specify in advance. All right, so these discovery procedures might identify latent patterns, clusters, dimensions, categories, recurring components. Some methods group similar observations together, and others learn continuous dimensions along which observations vary. This discovered structure can enter measurement in two ways. So oftentimes this discovered structure is informative, but sometimes it might be kind of a bit noisy or loose. You might want to use it as an input into a more precise construct definition. And you're going to use kind of the output from a discovery process to formulate a more precise concept. Importantly, you'll need to measure that on a separate sample to reduce post-selection inference concerns. Or maybe this discovered structure is itself the measurement output, in which case you're going to interpret it through interpretability methods, high-dimensional statistical analysis, and perhaps external validation. So discovery is useful when, as a researcher, you're unsure what to look for, you suspect existing conceptual categories are incomplete, or as a way to discipline discovery by pre-specifying a data-driven procedure rather than pre-specifying what you're going to measure. And so I think a great example of when this might be useful is, let's say you're going to run an experiment and collect a survey afterwards. You want to have an open-ended response question. If you pre-specify what you're looking for, it kind of defies the point of having an open-ended response. But what you could do instead is pre-register a procedure to identify recurring themes in the open-ended survey responses. And that way you keep the spirit of an open-ended response, but you can still pre-register. All right, so construct definition. How should a given concept be operationalized for a particular research setting? And this is actually quite difficult if the concept's multidimensional, not directly observed, closely related to other phenomena. So for example, we might want to measure trust, but what is that? It's some high-dimensional latent concept. You want to capture whatever dimension of trust is relevant to the research question and not simply proxy things like institutional quality, income, or other correlated variables. Okay, so AI is not going to determine construct definition on its own, but it can reduce the costs of data construction if zero-shot models perform well. It can both expand the candidate set of measures that researchers can examine and the empirical evidence that we can use to choose amongst them. Okay, so the AI needs to be combined with theory or with domain expertise that clarifies what the construct should capture for the research question, what it should be distinct from, where it should be stable, etc. Okay. So in observation, the role of AI is to serve as a scalable measurement technology. In observation, the researcher has a specified kind of definition in hand, and they want to apply it repeatedly to high-dimensional inputs at a low marginal cost. And AI is ideal for this. It makes it possible to classify large text corpora, to extract information from vast collections of images, satellite data, and more generally to construct low-dimensional features from unstructured data on a vast scale. And so, importantly though, there's choices that you have to make. You know, choosing the model, the prompt, the training data, input distributions. Apart from defining the concept itself, kind of taking the construct that's given, you still have to make choices to implement the AI, and those can produce different measurements. If there are errors, they are unlikely to be classical. You get systematic biases from the network architecture, from the distribution of training data, from implementation details. A neural network is taking nonlinear transformations at every level of the neural network. That violates classical measurement error. People are oftentimes doing binary or multi-class classification. That violates classical measurement error. There's no reason to expect this measurement error to be classical. And if the AI is making biased predictions, that will propagate to estimates of the target parameter. So an implication of this that we argue is that validation is central to AI-enabled measurement. Okay, so I want to turn now to first saying a word about the role of validation more generally in measurement, and then talking about validation across the measurement pipeline. Okay, measurement, remember, does not aim to reproduce reality. So validation cannot show that a measure perfectly captures a latent concept or recovers some fundamental truth. You know, sometimes I've had people push back against the importance of validation because they say, well, that's a latent concept. You can't show that you've accessed the truth, so why are you doing this? Well, we have kind of more modest goals that are still useful. And so measurement is aiming to construct a simplified representation. In principle, we would like to validate whether the measurement is useful for inference about the high-dimensional world. For economic questions, that's often quite difficult, at least in the short run. The underlying reality is complex, it's partially unobservable, it's multi-causal, it's not easily manipulated. And so again, we have kind of a more modest goal. We want to judge whether measurement provides a useful guide to reality, but to do that, what we're going to do is state an explicit measurement criterion and assess how well the measure behaves relative to it. And this is true kind of at all stages of measurement. And this criterion is stated explicitly. It can be interpreted, it can be audited, it can be debated, it can be refined. Okay, and so some people again might say, well, what's the value of anchoring to explicit criteria? I think that this is particularly valuable in the age of AI because it addresses some of the key limitations of AI. And so with neural networks, the internal mappings from the inputs, so let's say the text that you put into the language model and the outputs, the prediction of what's the topic of this article, are too complex to understand by inspecting the parameters. With an open source model, you could open it up and look at the millions to billions of parameters inside, but that won't help you to make sense of it very easily. Learned criteria are not expressed as explicit audible rules. And the biases of neural networks shift in complex ways with the inputs. Humans are not good at predicting these shifts, at least compared to how good they are at predicting how the accuracy of humans shifts with the input distribution. And so validation is making AI interpretable, not by elucidating its inner workings. If we as economists could do that, we could answer all the biggest questions in AI. That's a very challenging problem. Instead, what we want to do is make AI interpretable by evaluating its outputs against criteria that are specified by the researcher and justified by the researcher that are important to answering the research question at hand. And so validation also addresses the abundance of measures that AI can cheaply produce. Measurement choices, when you can produce many measurements cheaply, become objects of empirical comparison. And so validation provides explicit evidence for choosing amongst candidate measures, for correcting or refining measures, and for deciding when additional investments, like maybe training your own customized model, training a larger model for longer on more data, these are all costly investments that will improve neural network predictions. Validation can help you decide if these investments are worth it or not, given your measurement objectives. Some people will criticize validation because they'll say, whoa, wait a minute, why are you privileging humans when humans are noisy, error-prone, etc.? Well, validation is not privileging humans per se. It's privileging explicit interpretable criteria over implicit decision rules learned by a black box model. So yes, the validation data can come from human-coded labels. They might also come from scientific instruments, from administrative data, from theoretical predictions, from algorithmic criteria, etc. Even when a neural network is prompted or trained to apply a given criterion, its internal decision rules are not directly interpretable, and there's some evidence that while sometimes it does this well, oftentimes you give it a specific a set of criteria, and it can actually drift back to kind of what it's learned in pre-training, which is not necessarily what you may be after for your research question. Another potential critique of validation is it's imperfect. There will inevitably be edge cases about which reasonable people may disagree. This does not imply that validation lacks value, but it identifies where refinements may be needed. A neural network will encode richer information than a criterion that you state, but the question is, does this suggest a better interpretable construct, or does this richer information mostly encode things that are irrelevant or that are confounding variation in the context of your research question, or that are difficult to interpret? All right. So finally, I'd like to speak about validation across the measurement pipeline. Okay, because the 3 stages of measurement involve different sources of uncertainty, validation will take different forms at each stage. So discovery asks, has the exploratory procedure uncovered meaningful structure? In construct definition, we ask, does the operationalization capture the intended dimension of the concept? And in observation, we ask, does the measurement procedure accurately implement whatever criterion we selected through construct definition? All right, so first I want to talk about validating discovery. So in data-driven discovery, the researcher has not yet specified a fixed criterion against which the output can be validated. The entire point of it is you don't want to say, I'm looking for these particular things. Instead, you kind of want to let the data speak about what it contains. And so with validating discovery, we want to ask, has an exploratory procedure uncovered meaningful structure? We want it to be meaningful enough that we can actually interpret it. If we can't interpret it, what's the point? We might want to refine it into a construct, or we might want to use the output of the discovery process as the measurement object itself. Okay, so the most kind of straightforward way that we would validate data-driven discovery is internally. We want to know, do the data actually exhibit separable structure under a particular algorithm or representation? So how you validate this will depend on what method you're using to discover patterns in the data. For example, if you're using clustering, so you're grouping kind of texts into different clusters, you might say, well, does the output show within cluster cohesion and between cluster separation? Internally, we also care about stability. So meaningful structure should recur under perturbations of sampling, pre-processing, implementation, etc. All right, beyond kind of those internal validity concerns, a related concern is, does the discovered structure just reflect the method that we use to elicit it rather than a meaningful dimension of reality? And so there's a highly cited paper in psychometrics all the way back from 1959 by Campbell and Fisk, and they developed what they call the multi-trait, multi-method framework for validation. So they argue that a measure should converge with measures of related concepts, remain distinct from nearby phenomena that you want it to be distinct from for your research question, and be recoverable using alternative methods, which is the multi-method part of the framework. So what would this look like in AI-enabled discovery? Well, you might ask whether the structure that you've discovered, the way that you've grouped the data or learned about the dimensions of the data, can be recovered through different measurement routes. So you might vary the representation model, like what neural network model are you using to group the data? You might vary the discovery algorithm. You might vary the method that was used to elicit or compile the underlying raw data, or you might vary the underlying raw data source. And the more you see the same patterns kind of arise, regardless of the exact method you use, kind of the more plausible that you are uncovering a real pattern in reality and not just uncovering some sort of artifact of the method. Okay. You could have a great discovery process, but if you can't interpret the output, there is no point, right? And so a discovered representation is useful when we're able to interpret it. We see this in older traditions, but it's important as well in modern AI and representation learning. And so you'll see a lot of people use LLMs to cheaply generate labels or summaries or explanations for the discovered structure. And these methods can be really powerful, but it is important to caveat that the interpretations themselves should be validated, since the model's internal reasoning is not directly inspectable. When possible, external validation can also help with an interpretation. And so you might just interpret things by collecting a small manual audit sample, but on top of that, many papers will try to do some type of external validation. And so an interpretation of the discovered structure that you propose becomes more credible if it correlates with or predicts or remains distinct from external variables, that it should relate to or not relate to if the interpretation is correct. And so this external validation data disciplines the interpretation of a discovered structure. An important concern when you're doing data-driven discovery is post-selection inference. Data-driven discovery can be vulnerable to overfitting, cherry-picking, ex-post narrative constructions, et cetera. So how do you avoid this? Well, the first way is to do sample splitting. So you separate discovery from subsequent measurement. You use one split of the sample to identify candidate structures, and you use those kind of to understand the patterns in the data. Based on that, you refine what you want to measure, and then you implement that measurement in a separate sample split. Alternatively, maybe the discovered structure is the measurement itself. And so in that case, credibility depends on evidence that the structure is well-defined, stable, robust, interpretable, externally meaningful, and you can use tools like high-dimensional statistics to do direct testing on the discovered structure. All right. So that's validation of data-driven discovery. I want to turn now to what validation means in the context of construct definition. And so in construct definition, we want a theoretically meaningful concept to be concretely defined and operationalized for a specific research setting. The seminal work on construct definition comes from psychometrics, all the way back in the 1950s. There's this work by Kronbeck and Mehl, which is one of the most highly cited papers in psychology and psychometrics, which argues that many important concepts to social scientists are latent and high dimensionals. So examples would be things like trust, respect for authority, social capital, intelligence. You can come up with some rubric to measure them, but how do you know that you've actually captured that characteristic when it isn't directly observable or verifiable, when it's very high dimensional and you could be capturing many different dimensions of it, et cetera. And so their key insight is to argue that when direct observation is impossible, validation must be indirect. Okay, and so they argue that a construct is validated not by a single observable variable, but by a broader pattern of relationships that's suggested by theory or by the existing literature. They call this a nomological network. The idea is that you use theory to say, for instance, what the measure relates to. That's called convergent validity. What the measure should be distinct from. That's called a discriminant validity. And also things like how stable it should be, et cetera. And so if we wanted to kind of formalize this with econometric language, the way that I think about it, although they don't formalize it in this way, but I think about it as analogous to partial identification under theoretically motivated moment restrictions. So if you have a high-dimensional latent concept, not directly observable, no single restriction establishes that you've captured the intended construct, but additional restrictions can narrow the set of plausible measures. Traditionally, economists didn't worry about this because we emphasized things where direct validation was plausible. We measured prices, schooling, employment, revenue. But this is changing, and in recent years, economists have increasingly studied latent high-dimensional concepts where construct validity is much more contested. Things like trust or social capital or economic policy uncertainty. And so AI has the potential to improve construct validity by making empirical assessment of things that are difficult to validate more tractable. If it performs kind of well enough off the shelf, we can use it to generate more candidate measures and to also measure observable implications of the nomological network that can be used to test which measures are plausible. But AI also makes it essential to develop empirically grounded methods for assessing construct validity. So here's an example. I took economic policy uncertainty, a concept that's defined by Baker, Bloom, and Davis. I took their rubric as an example, and I asked frontier language models, GPT and Opus, to give me a definition of economic policy uncertainty. I did this 10 times. They go, they search the literature, they come back with something that sounds plausible, and then I implement that rubric. I mean, you can see that these are positively correlated, but they're certainly not perfectly correlated, and it does, matter potentially for the downstream conclusions and whether those are the same as the ones reached by Baker, Bloom, and Davis. And so if we just have this, which is very cheap and very easy to do, and people are increasingly doing this, we have no idea, really, if this is slop or if this is capturing meaningful variation in the concept. And so I think, at its core, this moves the problem of searching across regression specifications, from the 1990s to searching across representations of the underlying reality. If we don't have a principled and widely accepted method for construct validity in cases where what we're measuring is not directly observable, I think it risks encouraging p-hacking with AI slop on the one hand, while promoting nihilism about what can actually be learned about a high-dimensional world on the other hand. I mean, this is already happening to an extent, and I think that this is going to get worse without taking these issues seriously. Common critique of construct validity is that it depends on sufficiently developed theory, which we sometimes lack. If we don't have any theory at all, we may be better off just doing discovery, right? If we don't have a way to validate, have I actually captured what I'm trying to capture? You do data-driven discovery, you can learn some things about what you're trying to measure rather than developing a construct that is under-validated. Okay, in the final few minutes, I want to talk about observational validity. And so I think it's really important to distinguish construct validity and observational validity. And how I came about this is I have some work on observational validity, and I found kind of the most common critique from applied researchers was, well, construct validity is a big problem, and you're not addressing that, so why should I care about this framework? Well, actually, they're two separate problems, and they're both important. So I think of observational validity, which asks, does a procedure correctly implement the operationalization that you've chosen, as in some ways akin to internal validity, credibility conditional on a specified target. That's a construct definition in the case of measurement. It's an estimate in a given setting in the case of causal inference. I think of construct validity as analogous in some ways to external validity, whether the target answers your broader research question. And so, to validate observation, we start with the premise that researchers have access to a costly but credible criterion-based measurement technology for a subset of observations. This could be a measurement instrument, it could be human coding, etc. The criterion may be flawed, but it's interpretable, and we're going to take it as fixed. And so credible criterion-based measurement is often costly, so it may be feasible only to apply it to a modest sample, but we'd like to use a much bigger sample, so that we have more power, and we can do that with a black box technology like neural networks. We might use an LLM, a computer vision model for satellite data, etc. This scalable technology doesn't need to be AI, but in this lecture, we'll assume that the scalable technology is AI. And so in short, you have this accurate criterion-based measurement. This might be, say, ground station data, but it's very costly. And then you have this very cheap measurement that you can scale to a large sample, but it's a black box. And so a validation sample contains observations for which both the scalable measure and the criterion-based measure are observed. And under appropriate assumptions, this sample can be used to characterize the measurement error. And if you have an appropriately defined validation sample, it allows you to estimate the target parameter consistently and efficiently in the much, much larger sample, even under non-classical measurement error. And as long as your cheap measurement technology is good enough, you'll get a lot more power by using the much larger sample. One note that I want to make is that observational validity is not a sensitivity check. Sensitivity analysis asks whether conclusions change across different observational procedures, whereas validation links measures to an explicit criterion. It provides a benchmark for interpreting robustness checks. So these are both important, but one's not a substitute for another. Sometimes people will argue, well, I ran this through a bunch of AI models and they all agreed. Isn't that showing that my results are robust and this is good enough? Unfortunately, there may be correlated errors across models. Models, AI models are basically all using the same architecture or transformer. They use similar training procedures. They're basically all trained on a snapshot of the internet. You might use similar prompting choices. So really the takeaway is that agreement across AI agent measures may reflect shared biases rather than the measurement quality. This obviously means that you can't necessarily use one as a valid instrument for another. Kind of more generally, there's an emerging machine learning literature on response homogenization that argues that pre-training makes models broadly competent in similar ways. Reinforcement learning with human feedback pushes them towards similar preferred answers. With output variation driven more by prompting. And there's some social science evidence as well that by varying the prompt, which I think in many ways is varying the construct, you can get kind of many different answers to the same questions. And so I show this with a rubric we created. Is this historical newspaper article about politics? We had newspaper articles double labeled, created a big sample. And so that we have the ground truth for a large sample. And then we ran this through different frontier models, as well as kind of testing our own fine-tuned model at the bottom. And you can see that the prediction error conditional on our ground truth label is highly correlated across models. Prediction error is not random. And if we look at the mean share of articles about politics in our large labeled sample, on the far right, that's the oracle. That's the kind of the truth from applying our rubric. It might be a flawed rubric, but it's how we define politics. And you can see all the frontier models are overestimating the share of politics in historical newspapers. Why are they doing that? Well, I think it's this critique that, we give them the explicit criterion, but they fall back on their pre-trained knowledge. And so they've been trained on the internet. They might think a historical news article is saying, there's a measles vaccine clinic downtown today from 1967 is about politics because people are often making a political statement about measles today, but that doesn't mean it was about politics under our rubric, right? And so what we'd ideally like is to have a way kind of to do debiasing where no matter what model we use, we get the same estimate. It may be noisier if the model's not very good, but when we debias, we'd like to be able to get a similar estimate regardless of our model, and that's what I'll be talking about after the break. Thank you.
I'm really excited to be here. And so Melissa, really laid the stage for all of the parts of our plans for this methods lecture. So I'm going to spend some time talking about how we can do discovery and hypothesis generation with unstructured data. And really my starting point for thinking about this problem is just a broader observation that has gotten me and so many researchers across many fields very excited over the last year. And that is, if you look across fields, across science, AI and machine learning are increasingly accelerating the pace of scientific discovery. Just last year, we had AI models for the first time winning a gold medal in the IMO competition. And 1 year later, we have people posting memes about using AI models to break frontier conjectures in mathematics. In biology, AI is being used to predict novel protein structures, and more broadly across the sciences, researchers are using these tools to surface patterns that we as humans may not notice ourselves. So, and a question I've been deeply excited about for a long while now is that if this is happening in other sciences, what might this look like in economics? If AI can be used to accelerate discovery elsewhere, how might AI accelerate economics research? And of course, there's not going to be one single answer to this question, and there are many people doing wonderful work thinking about this problem. One answer might be that AI could accelerate existing workflows that we have. So for example, in empirical research, there's been a lot of really wonderful work trying to argue that we could use AI tools to automate parts of empirical analysis or policy evaluation itself. In econometric theory and in economic theory, we could use AI to help us formalize arguments, suggest new results and proofs, just as researchers are doing in mathematics. But what I want to spend the next 40 minutes or so talking about is that AI gives us the opportunity to formalize and accelerate a new type of problem that we can work on at scale. And that problem is what a burgeoning literature refers to as the problem of hypothesis generation. And this opportunity rests on really three observations about how AI and machine learning interacts with economics that a large set of researchers have built up over about a decade, really thinking on the machine learning side. So the first observation is that in many of the structured domains we study, machine learning algorithms often outpredict our best economic theories out of sample. And this is true in some of the most classic experimental settings where we study models of decision-making under risk. We study models of strategic interactions with game theory. And in light of this finding, researchers have then been excited to try to answer the question, well, if these algorithms are outpredicting our theories out of sample, what signal have these algorithms uncovered that we as researchers failed to notice? How could we extract theoretical insight from this black box? The second observation is that, of course, while we care about doing well in prediction within domain or generation within domain, economics is far more than that. We care about trying to generate theories and ideas that generalize to new settings, that allow us to evaluate counterfactuals and more broadly understand mechanisms. And there's been a lot of work pointing out that algorithms on their own may fail on this margin. So we want something else than just an uninterpretable black box. And the last observation is one that I think everyone in this room has wrestled with, and that is that in economics, we always are confronted with the lamppost problem. We search where the light is in our structured data. The closed survey items we collect, the typical outcomes we study in a randomized experiment, the fields of an administrative extract, only capture a limited part of the domain we study. And as a result, for a long time, there have been huge incentives for researchers to try to use unstructured data to record features that we did not measure before in our structured fields. And this is an extraordinarily incomplete list, but there are wonderful examples of this across every single subfield within economics. So together, these three observations about how AI and machine learning could interact with economics suggests a very exciting opportunity. Could we use AI to analyze unstructured data to try to automatically discover what we should be measuring at scale and how it relates to the quantities we care about? This is an activity that this literature refers to as hypothesis generation. And then once we've generated these hypotheses, can we use them and analyze them using our standard empirical and theoretical toolkit? Can they give us the fodder that we can then ask the typical questions we want to study in empirical economics? So as I'm going to argue and point out and hopefully summarize for you, over the last really 3 or 4 years, we've seen more and more examples of researchers in economics, computer science, statistics, data science, a wonderful interdisciplinary mix of researchers building algorithms to assist us or automate the process of hypothesis generation from unstructured data. And I want to anchor that conversation around 3 empirical examples that I'm going to keep going back to throughout the talk. So one important area where we've seen machine learning interact with economics is in a class of problems that people now refer to as prediction policy problems, which start from the observations that many important and consequential decisions we study hinge on a prediction. So for example, in pretrial release, a judge decides whether to detain or release a defendant based on a prediction of whether that defendant would commit pretrial misconduct. And for example, in child protective services, an agency decides whether to open a case and provide services for a family based on a prediction of whether the child suffers from underlying maltreatment. So the first example is going to focus on the context of pretrial release. And in pretrial release, though judges see more about a defendant than what is captured in any structured administrative extract, after all, the defendant is in the room with them and they get the opportunity to ask that defendant many questions, machine learning algorithms trained on structured data to predict misconduct risk systematically outperform judges in making these decisions. And this is a point that's been made going back to some classic work by Kleinberg et al. In the mid-2010s and has been followed up in many different jurisdictions. So it would appear that judges are getting these decisions wrong, but what exactly are they getting wrong in making these choices? So in a wonderful paper, Ludwig and Melanathan try to answer this question by turning the camera on the judge, and instead of predicting misconduct risk, let's predict detention decisions in Mecklenburg County, North Carolina. And their starting point is the observation that the single most important predictor for a pretrial detention decision is the mugshot. Above and beyond structured information about the defendant, such as their current charge, their prior record, demographics, including age, race, and gender that you would think are inferred for the mugshots, known facial features in a large psychology literature, and even incentivized guesses about who is going to get detained from the mugshot. In fact, about 78% of the predicted signal from the mugshot is entirely unexplained by structured characteristics in administrative data or known facial features that you might code from this image. So it appears that something unnamed in the mugshot is systematically driving detention decisions. What is it? The next example I want to talk about goes to a different setting, in Child Protective Services, where in Child Protective Services, an investigator has to decide whether to open a case and provide services to a family based on a prediction of whether a child is suffering from maltreatment. And here again, we can do a comparison of investigators against a machine learning algorithm, but you find something quite different. In this work I did with Jason Barron, Will Doby, Richard Lombardo, and Joseph Ryan, what we find is that in Michigan, in fact, a substantial fraction of investigators, about 36% of them, significantly outperform a machine learning algorithm trained on structured characteristics. You can spend a lot of work trying to unpack that result, and what you find is that the gap between investigators and the algorithm is not explained by anything that you have in your structured data. Something else is separating the very best investigators from the worst ones. So what is it? Well, of course, investigators do a lot more than what's captured in the structured data we have. They visit the home, they interview the family, they contact teachers and doctors. None of this is captured in the typical structured data available in administrative systems. But what we do have available is that investigators record rich, unstructured case notes that document everything they did during their investigation. So we could then try to ask the question, can we use these case notes to try to generate hypotheses about what differentiates high versus low performing investigators? Do they do something or notice something differently in the investigations? And does that help us explain heterogeneity across decision makers that we otherwise couldn't explain? And as a last example, to give you a flavor, this is not just a question you can ask in applied micro. Let's think about hypothesis generation in studying household expectations about macroeconomic outcomes. Of course, how people explain the macroeconomy shapes their expectations, and those expectations in turn drive their behavior. So in a wonderful recent paper, Andre et al. In the Review of Economic Studies tried to understand what are the inflation narratives people held during the 2021 to 2022 inflation surge. The narratives shape people's inflation expectations because it affects how they interpret the news. For example, if they think that inflation is caused by an energy crisis, which led to supply chain issues, that might lead them to interpret future events differently. So they wanted to start by just asking, what are the narratives that people actually hold about the causes of inflation, not the ones that we as economists might ex ante write down ourselves? So to do that, what the authors did is they elicited a lot of open-ended survey responses. As I briefly hinted at, that's an essential step in this activity. An ex ante menu of these inflation narratives would presuppose the very narratives we were trying to discover, and there's no reason to think that the ones that we as economists might generate are actually the narratives people hold. But it led to a very painstaking process where the research team then had to read every single response themselves and hand code them into a directed acyclic graph. This is only going to become more popular. Collecting open-ended responses is increasingly common in economics research and will become increasingly cheap as there's wonderful work trying to develop AI interviewers to do open-ended, unstructured interviews with subjects. So rather than having a human try to look at these narratives and generate hypotheses about them, could we hand the responses to some AI pipeline and let it discover inflation narratives automatically? So this is a nascent and extremely rapidly growing space, as I mentioned, that sits across fields. There's examples in economics, medicine, education, computer science, computational, social science. So this is going to be an imperfect attempt to try to summarize this literature in about 30 minutes. And it's also going to be particularly dangerous because the frontier of AI is moving extraordinarily rapidly. And what was impractical in this problem may now work today. It was impractical a year ago, may now work today. So my goal is going to be to try to very briefly describe the structure of hypothesis generation procedures, some of the key choices that are required, and some of the challenges that arise. But I will, of course, have to skip details just due to time constraints, but the slides are online. So what's the setup? We're going to think about this problem in a context where we have access to some data, X, and an outcome that we're interested in studying, Y. And each unit of data, X, is going to be a piece of unstructured data. Think of it as images, text, audio, etc. So in Ludwig and Melanathan, X is a mugshot, and Y is the detention decision. In Barron et al., X is the case note written by an investigator, and Y is the case opening decision. And in Andre et al., X is the open-ended response, and Y is the respondent's reported inflation expectations. So we observe some unstructured data paired with some outcome Y. And as a starting point in this hypothesis generation exercise, the researcher is going to choose a candidate space of hypotheses, script H, that they want to try to generate into. At a very high level, each hypothesis is going to name a feature of the unstructured data that we could potentially go out and measure at scale. Roughly speaking, you could think of that as some function that's going to map this piece of unstructured data to some numeric value. And it's often an indicator for whether it exhibits a particular feature. So in these problems, we can describe the candidate space of hypotheses at a very high level. In Ludwig and Melanithin, it is descriptions of facial features. In Barron et al., it is descriptions of narrative evidence themes expressed in the case notes. In Andre et al., it is descriptions of causal narratives about inflation. But the core challenge is that we cannot ex ante specify every hypothesis contained in this space. It's an implicit object. If we could do that, it would effectively mean we could enumerate everything we could possibly hope to discover from unstructured data. And if you're familiar with the broader literature on automation, this is really a version of Polanyi's paradox. We can recognize hypotheses when we see them, but we can't ex ante list them in advance. And that's going to be a core challenge in building procedures to do this. So at a high level, I think of a hypothesis generation procedure as something G that's going to take in input data, pairs of unstructured data associated with some outcome Y, and then return a collection of hypotheses H hat to the researcher alongside with some evaluation metrics that assess their quality. So in Ludwig and Melanithin, we're going to take a data set of mugshots and detention decisions and return a collection of descriptions of facial features. In Barron et al., we're going to take a data set of case notes and case opening decisions and automatically return descriptions of narrative evidence themes in these case notes. And in Andre et al., in a reanalysis, we're going to take these open-ended survey responses and inflation expectations and return descriptions of causal narratives about inflation. So at this point, everything I've said, this hypothesis generator could just be a black box. It's anything that maps data to named hypotheses. So in principle, this could be the researcher. That's really how we have operated for the last decades, hundreds of years. Tomorrow, perhaps this is just a frontier AI model, make a procedure call to OpenAI, and maybe that's our hypothesis generator in the future. But so far, how this literature has approached this problem is that many of the hypothesis generation procedures we write down share a common structure to them, and they typically organize this problem into 4 stages. There's going to be a first stage where we try to score each unit of unstructured data. Then we use our scores to try to contrast units of unstructured data that are high scoring versus low scoring. Then we try to interpret what separates these high versus low scoring units of unstructured data, and then we're going to report some evaluations on a held out test sample. So my goal is to try to walk through each stage at a very high level, discuss how these are implemented in 3 examples, and some of the key challenges and choices that arise. And what I want to flag up front is that, as I mentioned, this is a nascent space. So each of these stages admits many implementations, and often the choice of implementation is going to depend on the domain and the specific data modality, whether we're talking about images, texts versus waveforms. And to this point, for folks interested in methodological problems, there's been very little systematic comparison of these choices, and I'm going to come back to that at the end. But what's going to be important is that at the evaluation stage, implementations are going to be judged in largely the same manner. We're going to ask, do the generated hypotheses correlate with the outcome of interest in some held out sample? So effectively, we're going to fall back to a supervised learning problem where within domain, there's going to be what's effectively a verifiable common task, in the words of David Donahoe, where we're going to ask, are we producing hypotheses that explain variation in the outcome we're interested in studying? So let me first very briefly talk about the scoring step. So the scoring step is going to try to construct a score, and I'm going to denote by R of X, which is going to associate each piece of unstructured data with a number or a vector. And what that's going to do is the score is going to turn unstructured data into something that we can now systematically compare. We can try to look for what are differences in the unstructured data that lead to changes in this score. There are many common choices of this, so let me just highlight 3 of them that you see in the literature so far. The first would be to define the score as the outcome itself. This is the simplest choice. If we're just trying to study a binary outcome, whether a defendant is detained or released, a case is opened or not, we could group unstructured data by whether it is a case note associated with an open case or not. The second might be to define the score to be a learned predictor. Let's predict the outcome of interest using the unstructured data. So for example, let's score each mugshot by how its predicted detention risk. And the value of this is going to be a ripple through downstream in some choices that we can eventually make. And the last choice you see would be to associate each piece of unstructured data, reduce it to an embedding. In other words, let's try to place this unstructured object into a numeric vector space, where in that space, nearby points are going to, roughly speaking, express similar things. And that's going to be, has some familiar ancestors to ideas in topic models. So how do you think about this choice? Well, let's first think about the choice between the outcome and predictions of the outcome itself. I think in general, there's probably no reason to use the outcome directly. The smooth score is usually preferred. We usually think of outcomes in these sort of social science settings as noisy, and trying to predict the outcome using the unstructured data attempts to preserve only the variation in y that is explainable by the unstructured data we observe. And furthermore, this is going to open up avenues downstream when we do hypothesis generation, because having a predictor would allow us to score units that never appeared in the data, which we can then exploit later on. An embedding sort of sits in a different category because each unit is now associated with a point in a multidimensional space. So what would be an example? In Barron et al., we could try to take case notes, embed it in a space, an embedding space, where we would hope that case notes that describe domestic violence are going to cluster together far away from case notes that describe housing conditions that the child is experiencing. Now, when you do this, each direction in this embedding space is now a potential score. We could try to ask how much does a particular unit x align with some dimension in this latent space. So that still sort of punts on the question, because now you have to pick a direction in this complicated space and then decide how to interpret it. One idea that you'll see in this broader space on machine learning and AI is that embeddings often behave more like an index. If you think about directions in an embedding space, they often bundle several concepts together at the same time. People sometimes refer to this around the jargon of superposition and polysemanticity. But as a result, when I talk about embeddings, I'm often going to refer to a class of models that people refer to as sparse autoencoders, which attempt to take some pre-trained embedding and unbundle that index, re-express it in a sparse embedding space, and then interpret that directly. But that's a detail we'll come back to later. So once you've picked a score, the next step in hypothesis generation procedure is what I'm going to call contrasting, which attempts to use the score to construct a set of examples E, units that differ along the score R of x. The working presumption in this literature is that hypotheses can be labeled by inspecting differences. If we have examples that differ along the score x, we could pass that along to some human or an AI agent, and that would be easy for them to try to label what are the differences between the objects in that set. Again, this is Polanyi's paradox appearing. We can recognize hypotheses when we see them, but we can't ex ante generate them all. At this point, there are really three common strategies you see in the literature for producing these example sets, and each of them is going to return a different one. The first is what I'm going to refer to as morphs. Let's try to generate a counterfactual pair, unstructured data x and x prime, by moving along the gradient of the score inside a generative model of the data. I'm going to make that concrete in a little bit. The second is what I'm going to refer to as tails. Let's pick two real units in our sample from two tails of the score, high scoring units and low scoring units. That's going to give us two sets that we can kind of contrast. And the last one is I'm going to refer to activations. Let's pick real units that are selected based on a sparse autoencoder's embedding space. Units that are going to score high along one dimension in that embedding space. As you can kind of see, each of these different contrasting strategy leans on a different choice of what's the scoring function. Morphs are going to require us to be able to score units that don't exist in the data, so you need a predictor of the outcome given the unstructured data. Tails are going to rank observed units, and activations are also going to rank observed units. So this is all very abstract, so let me try to make this a bit more concrete by illustrating some of these choices in the examples that I mentioned. So first, let's think about Ludwig and Melaynethan. So for them, in their hypothesis generation procedure, the score is a convolutional neural network that they train to predict detention decisions from the mugshot alone. They're going to try to construct a contrasting set of examples through morphing. Let's construct pairs of mugshots that are close to one another but differ on this score. And again, the idea would be that if you just randomly sampled faces, they're going to differ in many different ways, and it might be hard to really inspect what are the differences. So how are they going to try to operationalize this morphing idea? Well, let's start with the simplest idea. Let's take a mugshot and just follow the score's gradient in pixel space. The score's gradient in pixel space is the direction that most increases predicted attention, so that seems like a very reasonable place to start. If you do that and implement it literally, you produce something that is decidedly not a face. So we started with some synthetically generated mugshots, updated each pixel in this image along the predictions of our trained convolutional network. Clearly, you end up with something that's a little more haunting than a photo of a face. So what went wrong? What went wrong is that when we think about unstructured data, this is a really rich space. In the space of all possible images, think of 500 by some by 500 some matrices or tensors. In the space of all possible images, real faces occupy an extraordinarily low dimensional manifold. And so if you take any direction in that space, you're going to be stepping off this face manifold. How could we fix that? Let's fix that by building a generative model of the mugshot distribution. In this paper, a generative adversarial network. There's backup slides. There's a lot of resources on the internet to understand what those ideas are. But let's build some generative model of the mugshot distribution. And rather than morphing pixels, let's try to morph in the latent space of that generative model. And so the idea would be, let's now think about the gradient of our score through the latent space of this generative adversarial network, update in that, and then use the generative model to decode. And if you do that, you actually produce things that are sensible. So as a sanity check, what Ludwig and Melaynathan report is they say, well, we want to interpret our detention predictor. Let's start by predicting the age of the defendant, and then applying our morphing procedure to our age predictor. And if you do that, you actually produce morph pairs that allow subjects to pick out aging. So they started with the same original mugshot, now applied this morphing procedure to follow a convolutional network trained to predict age from the unstructured data, and produced a morph face that looks like an aged version of the one we started with. So now they're going to take this idea and then apply it to their detention predictor, and that's going to produce many pairs of an initial mugshot and a morphed mugshot that differ based on the predictions of this convolutional network for who is more or less likely to be detained. So it's important to note that this morphing idea, nothing here is specific to faces in detention. We can apply this idea in principle wherever we have a good predictor and a good generative model, we can morph. In a wonderful recent paper by Ziad Obermeyer and some co-authors, they apply the same technique to think about how could we extract features that are predictive of sudden cardiac death. And so to do so, they build a generative model of ECG waveforms and start morphing in the latent space of that generative model using a sequence predictor to predict sudden cardiac death from ECGs. So images and waveforms have good generative models. We can build those quite easily, and those generative models have latent spaces that we can manipulate and sample from. So you've heard about large language models, which are generative models of text. How could we do this with text as well? So let's go to the next example by Baron and our team of co-authors. What we did in this paper is we scored each case note, again, by predicting case opening decisions using off-the-shelf pre-trained embeddings of the case notes. So what if we tried to reuse the morphing recipe, which we would use a language model as the generative model of text? There's a whole separate conversation we could have about why that is actually a very non-trivial problem in the mechanistic or interpretability literature. And I will just bracket that off, but we'll be happy to chat with folks about why it's actually very non-trivial to steer in the latent space of a language model and then sample from it and produce things that are sensible. So instead, what did we do in this paper on case notes? Instead, what we did is we picked the second contrasting strategy, tails. We binned cases by predictions of case opening decisions using only the structured characteristics X. And then within each bin, so case notes that have the same predicted probability of case opening decisions, if you were just using structured information, we asked what are case notes that are predicted to be very likely to have a case opening using just the text versus very unlikely to have a case opening based on the text. And the idea would be this is a contrast set now where differences in the score are only reflective of differences in the text, not the structured characteristics that we already know and we understand how to interpret. As our last example, let's come back to this reanalysis of inflation narratives. So as I mentioned, this team of co-authors collected open-ended explanations of how households think about inflation. So as a starting point, I did this in one day using Codex. This is very simple. You can do it too. Converted each response from this paper into an off-the-shelf embedding. Just use OpenAI's off-the-shelf embedding models. And now once I have this embedding space, I have to ask a question, what's a direction that we should choose? So I'm going to pull from some recent work in computer science, which is a beautiful name, hypotheses, where I'm going to take the embeddings from my OpenAI model and produce a sparse autoencoder, which is just going to re-express this embedding space to have many sparse features. And now that gives me a candidate score, one per each dimension in this SAE's embedding space. To then select which direction you're going to focus on, I'm going to split the sample into a train set, a validation set, and a test set. On the validation set, I'm going to examine which SAE directions are most correlated with inflation expectations, and those are the ones I'm going to pick. And so then now my contrasting set are going to be the open-ended responses that score high versus low on the top 20 directions in this sparse autoencoder's embedding space. So once we've constructed these contrasting sets, we've now arrived at the point where we could try to start generating hypotheses. So this is the third stage, what I'm going to call interpretation. So as I mentioned, contrast hands us concrete examples of unstructured data that differ along the score. How do we go from these examples to hypotheses? So how do people generate hypotheses? Perhaps you do it in the shower, but I think the way we all do it is we do it by searching for differences in the world. We think about some outcome we want to explain. Let's think about observations that have high outcomes, observations that have low outcomes, and try to label the differences between them. And hypothesis generation procedures are just going to do the same thing using the contrasting sets that we just produced. So I'm going to call an interpreter iota, which is going to take the examples and then return hypotheses. And this is the stage that has been, by far more than anything else, changed by the, rapid progress in AI and large language models over the last year and a half or so. We have now a really meaningful choice over who the interpreter is. And so existing work really uses two stages for this interpretation. One are humans. Perhaps we would recruit subjects online to expect the examples and name the differences they see. That's what Ludwig and Melanithan did. In Obermeyer's analysis of ECGs, you can't just recruit people on Prolific to inspect differences in ECGs. You actually need to get doctors to look at them and name what are the morphological differences. So that's what they do. But in many other examples, perhaps an off-the-shelf large language model could do this quite well. And that's what we did in this work with Barron et al. And that's what we also are going to do in this reanalysis of inflation expectations. This, I think, is a fascinating question, how to think about the choice of different interpreters here. Different interpreters, when given the same examples, need not return the same hypotheses. And if you go to all sorts of work in AI, we have ample reason to think that humans and large language models carry very different inductive biases in what they notice from these sorts of examples. There's ample evidence that human and artificial intelligence really differ. And here, ideas and hypothesis generation connect to stuff that you may have heard about language models having jagged frontiers of intelligence, humans being very poor at trying to predict where language models will succeed or fail, or language models having their own sort of systematic reasoning errors that look quite different than the sorts of errors that people make. So once we've gone through all this process, we have scored our unstructured data, we've constructed our contrasts, we provided them to interpreters, we now have a handful of hypotheses. What do? We come to the last step of evaluation. So everything so far returns a collection of hypotheses, which are features that are expressed in the unstructured data. And evaluation asks a very simple question: how predictive of the outcome are these named features from unstructured data? And as a result, evaluation looks a whole lot like a very standard supervised learning evaluation problem. Let's have a holdout test set and just evaluate how well we can predict the outcome on the test set using these generated hypotheses. And really the core idea here is that if our hypothesis generation procedure never touches our holdout sample, it really does not matter to us how we produced hypotheses. If things are nice in IID, if we randomly hold out a set of examples, we can evaluate the performance of these hypotheses on this. And as a result, I really think about so far evaluation has been centered on this common task that's really powered a lot of breakthroughs in AI and ML over the last 15 years or so. So what do people report when they go on the test set? First, they might report something that I'm going to call validity of each hypothesis, not to overload the word of validity in this methods lecture. But at a high level, this tries to answer the question, how correlated is this feature of the unstructured data with the outcome Y? And so if the outcome is binary, if the feature is binary, we might just try to ask, what is the average difference among units where the feature is equal to 1 relative to units where the feature is 0? Whatever you end up choosing, this becomes a very standard sort of inference problem on the test set. As Melissa flagged, many of these procedures can produce a large number of candidates, and as a result, corrections for multiple hypothesis testing are essential. So in one paper in computer science that tries to use large language models for hypothesis generation, they have a pipeline that produces over 3,000 generated candidate hypotheses, and then when they go to the test set, they have to apply pretty significant multiple hypothesis testing corrections, and only about 13 of them still remain significant. And then there's been some more recent work in the econometric side thinking about this multiple testing problem. Furthermore, the test set is not going to be the endpoint for us. We would like to select even the best performers on the test set for further downstream analysis. And this is where problems in hypothesis generation, perhaps connect back to ideas you've seen in econometrics on doing inference on winners. We would like to select the most interesting, most promising hypothesis for downstream analysis, so standard ideas from the selective inference literature can be applied on the testing set as well. A last benchmark people often report in this hypothesis generation space is what I'm going to call the completeness of the generated hypotheses. So our procedures take unstructured data, try to distill them down to lower dimensional structured features that we could try to measure. So it's valuable to ask how much of the signal in the original unstructured data have we preserved, or do our hypotheses still capture? And the idea is actually to borrow an insight from work at the intersection of economic theory and machine learning algorithms, and calculate something that people refer to as completeness. So what's the idea here is let's build a benchmark predictor of the outcome from the unstructured data itself. So in Ludwig and Melaynethan, that might be their original convolutional network to predict detention decisions from mugshots. And then let's also build some naive predictor of the outcome. And let's ask, how does the predictive performance of predicting the outcome using our structured hypotheses compare to the predictive performance of a model that just tries to flexibly predict the outcome from the unstructured data itself? And ideally, our hypotheses would preserve most of the predictive signal from the unstructured data that we started with. So I really am focusing so far, largely because that's what the work that's been done so far is focused on two sorts of evaluations we could report on a held out test set, validity and completeness. And I've really sort of taken the perspective that the hypothesis generation procedure was applied on some separate training sample, and we're then just treating the hypotheses as some fixed object. But in principle, I could have split the data in many ways, and so we could imagine resampling the data, doing different splits, and now the validity and the completeness of the hypotheses themselves are random, and their validity and completeness are going to be random as well. And so you could start imagine trying to build up ideas like an analog of size when we think about hypothesis generation, or thinking of completeness not as a property of hypotheses, but as a property of a hypothesis generation procedure. And I think there's really interesting methodological questions on how you might think of whether there's a trade-off between size and completeness when we're building hypothesis generation procedures. But I will leave that for the folks interested in those sorts of questions for later on. And the last thing I just want to raise is I've also really only focused on an evaluation of how well do the hypotheses predict the outcome of interest. That's both validity and completeness. But those are not necessarily the only desiderata we would want for the hypotheses we generate. For example, we might have a notion of wanting to generate novel hypotheses. Then it becomes a question of novel relative to what. In some work that I've done with Sendel Melaynethan, we thought about this problem in the context of how would we generate hypotheses that are novel relative to some structured parametric theory. And then sort of for methodological folks, we might want to then ask, are there trade-offs across these desiderata? How do we think about what it means to build good hypothesis generation procedures? So in the last 5 minutes, I want to now wrap this up by going back to the 3 examples and trying to show you what exactly do these procedures produce in these empirical settings. So let's go back to Ludwig and Melaynethan's analysis of pretrial release decisions. So at a high level, how are they going to partition hypothesis generation into these 4 steps? They're going to have a predictor that predicts detention decisions using mugshots. That's going to be their score. The way they're going to contrast, as I mentioned earlier, is they're going to build a generative model of mugshots and then start morphing that generative model along gradients of this detention predictor, and that's going to produce synthetic mugshot pairs. Then they're going to pass those synthetic mugshot pairs, they probably did this in 2022 before language models were a big thing, to some folks on Prolific to have them inspect the pair of mugshots and label what are the differences between them, and that's going to be their interpreter. It's going to produce some hypotheses. So here is one such example of a morphed pair that the authors produced. This is the same synthetic face moved from low to high predicted detention risk. So what changed? When they presented this to the interpreters in their study, the interpreters overwhelmingly produced a hypothesis of being more well-groomed. And it turns out that being more well-groomed is less likely to be detained, perhaps not the most surprising finding. But they can then play this procedure again, where now that they have generated the well-groomed hypothesis, let's now morph in a direction that's orthogonal to well-groomedness and produce new morphed pairs of mugshots. So this is, again, a synthetically generated mugshot and one that's now been morphed in the direction to have a higher predicted probability of being released, or a lower probability of being detained in a direction that's orthogonal to well-groomedness in their their GAN's latent space. This produces a second named hypothesis of defendants being more or less heavy-faced. And then when they go out of sample, it turns out that that is also enormously predictive of whether a defendant gets released or detained. So now they have two hypotheses of facial characteristics, well-groomedness and being heavy-faced or not. And so then the authors end by computing a completeness analog by pointing out that well-groomed, heavy-faced, and then all the other known facial features in the psychology literature together explain about 27% of the variation in their convolutional network. So in principle, there may be more structure here that the authors are not exploring in this paper. So what do the authors then do? Once they have the hypotheses, they spend probably many pages in section 6 in the appendix to try to probe the novelty. They present a bunch of sort of more standard empirical evidence that these hypotheses are new to the psychology literature, they're new to the crime literature, and they're new to practitioners, prosecutors, and judges. So what's interesting here is this is a setting where we used unstructured data and hypothesis generation procedures to discover a potential mechanism for judicial error in pretrial release. And as I mentioned, this method is general. Effectively, the same pipeline was applied to an ECG predictor of sudden cardiac death and actually produced a novel morphological feature of ECGs that's correlated with sudden cardiac death, which is quite frankly an amazing finding. Let's go to Barron et al., thinking about child protective services. There, the case opening predictor was our score. We constructed contrasts by binning case notes of those who are similar based on predicted case opening using structured characteristics, but quite different based on embeddings of the case notes. And then we passed them to a language model to read and name them. The LLM interpreters in this context returned 5 evidence themes that appear to consistently arise across case notes in a manner that's correlated with case opening decisions. The most interesting of them are explicit noticing of absence or ambiguity or contradiction of abuse evidence, or noticing evidence that is exculpatory, I can never say that quite right, exculpatory for the family. On a held-out sample, we can also report a completeness measure. These 5 themes actually turn out to explain about 84% of the predictive signal for case notes, for case opening decisions from the case notes. And what's even more interesting is that there are systematic differences in which higher performing investigators report relative to lower performing investigators. And in particular, higher performing investigators are much more likely to record in their case notes explicit reference of corroborating that there's adequate care for the family or that there is ambiguous or contradictory evidence relative to the initial referral. So it appears that the best investigators are reporting disconfirming evidence more often, which if you go to psychology is a classic corrective for confirmation bias and has been really extensively used in some recent interventions to promote system 2 thinking in consequential settings. Very briefly, let me just show you the results from reanalyzing inflation expectations. Here, I'm just going to pull something off the shelf from the CS literature, that Hypotha SAE paper, and apply it to their data. What we produce are about 20 SAE features that add substantial signal over structured covariates for predicting inflation expectations. And then from those SAE features, we can pass them to a language model to produce 20 named concepts that are related to inflation expectations. And those too add substantial signal for predicting. You can then try to correlate what are the AI-generated concepts relative to the author's hand-coded concepts. And what you find is there is a large fraction of the AI-generated concepts that really line up with what the authors hand-coded from their analysis of the open-ended responses. But there's a large subset of them that are not quite correlated. So perhaps there is signal here that is still interesting to explore. So for example, one of the themes that the language model generates based on the open-ended responses is whether a respondent explicitly refers to Joe Biden by nickname. That's very predictive of household inflation expectations, which you could think of as hyperpartisanship. So to wrap up, what I hope I convinced you just at a very high, very quick level is that we now have procedures that allow us to turn unstructured data into hypotheses. What's going to happen next? These generated hypotheses are now the fodder for downstream empirical work. They may give us ideas about what are interesting mechanisms to test, what interventions we should trial, or what are causal effects that we may have overlooked. So for example, in child protective services, would training lower performing investigators to search for disconfirming evidence improve decisions, which is an idea that's been explored in recent work on police misconduct. what I want to emphasize and leave you with is that the barrier to entry here is really low. I threw a lot at you in 40 minutes. The simplest version of this simply hands an LLM contrasting documents, asks it to name what differs, and then you, the researcher, inspect whether those are interesting and try to validate them out of sample. More elaborate versions are actually off the shelf. The SAE framework I told you has really nice, good packages. Yourself, Codex, or a very smart RA could do this themselves, and all of the embeddings I'm using are pre-trained off the shelf using API calls. What's really scarce here is actually your comparative advantage, which is finding economic settings where there is interesting unstructured data tied to an outcome we care about. And if you have that, you're off to the races to engage in this activity. There are many methodological problems here for folks interested. I'd be really happy to chat with you about them. I think more econometrics in this space is really valuable. And I want to flag that the frontier is moving rapidly. There is huge returns to deep interdisciplinary engagement with our colleagues in computer science and AI working on these problems. They have tools, they have ideas, they have algorithms, we have problems, and those two actually don't interface in a way you might expect. So to wrap up, once we have generated a hypothesis, we have to measure it. We have to turn this named concept into a variable that we can use across a full data stream and then plug those measurements for downstream estimates. So whether the hypothesis comes from a human or a machine, the next thing we're going to try to take up after the break is can we use AI to measure it at scale? And that's where we're going to spend the last half of this methods lecture talking about. So that's all I have for you. I think we have a break now until about 4:40, so 10 minutes or so, and then someone will ding a bell. But that's it. Enjoy the break.
All right, so I'm going to be spending this slot talking briefly about construct validity and then talking about observational validity. And you know, one of the things I've been told is that, oh, I'm not on. Are the sound people? Okay, is this working? All right, so as I was saying, I'm going to be spending this slot talking about construct validity very briefly, as well as observational validity, which is a much more developed literature. And you know, so one thing I was told is that, you know, the main reason people might choose to view the lectures or attend is they want to know, you know, how should I compute my standard errors? How do I run a differences in differences specification with AI predictive variables? And we're going to get to that in this 40 minutes, and I will introduce an R package for doing that. But before I get to those very practical questions, I'm going to spend just a few minutes talking about kind of a much more open area. Because I think it's important. And you know, I don't have an R package or a Python package or a Stata package for this. I don't even know exactly the right way to approach it, but I'm going to briefly talk about it because I think that it's a huge open area and very important. And so if you recall from my first lecture, construct validity addresses how a theoretically meaningful concept should be operationalized. There's conceptual uncertainty. And this is important because economists are increasingly measuring novel, latent, high-dimensional concepts that are not directly verifiable. And in the age of AI, we can potentially create many different measures cheaply. And that's great because we can explore measurement. We can also create more evidence for validating those measures cheaply. But at the same time, it raises this concern that I introduced with the Economic Policy Uncertainty Index, that you can create many different measures of the same underlying reality. And so which of those are valid and which of those aren't? We need to be able to answer that. I think it also raises another set of issues, which I don't have anything to say about, but that I just want to flag, which is that construct validity is use contingent. You might have a measure validated as a passive description that could lose validity once it's embedded in decisions and agents re-optimize. And because AI makes it cheap to deploy constructs in real time at scale, it could exacerbate this problem, essentially kind of an analog for construct definition of Goodhart's law. But I want to focus on construct validity as partial identification. And as I said, this is a pretty open area. I mean, people have thought a lot about this kind of philosophically, but in terms of having an econometric framework, there's you know, much less literature. And so the way that it seemed most natural to me to approach this as a first pass was to take the nomological network of Cronbach and Miel and apply that as a partial identification problem. And so remember, the idea here is that if we cannot directly validate a measure because it's high dimensional, it's a latent construct, it's not directly observable, we want to be able to kind of validate it with multiple restrictions to see which measures are valid and which it doesn't. And so the researcher has to specify the candidate measure. The researcher has to specify a set of moment restrictions that theory or the existing literature or knowledge of the context suggests that those measures should meet. Both require justification. Of course, this isn't giving a causal account of measurement, but it is helping to discipline it. And so I'm going to let X denote high dimensional reality. And a researcher considers a menu of different candidate measurement functions, with each candidate mapping the same underlying reality into a measure. Both the measures and the downstream estimates must be made comparable before we can do this exercise, which, you know, you might have an indicator and a scalar measure. You need to put them on the same scale. The downstream estimate beta also needs to be defined consistently so that you can compare measures, which is relatively straightforward. Now I'm going to define auxiliary observables that are implicated, you know, by theory, by our knowledge of the context. Again, we might have related quantities Z. We want the measure to correlate with them. We might have distinct quantities. We don't want the measure to capture that because that's something separate that we want to hold constant. We might have groups that should differ on the construct. So for instance, if we want to measure partisan speech, we want Republicans and Democrats to differ on that dimension of speech. And so with these variables, we can create moment restrictions. Convergent validity says that the measure needs to be correlated with the related quantities. Discriminant validity, it needs to be distinct from the things that we want it to be distinct from, et cetera. And you can make other moment restrictions as well. And so we're going to collect the threshold and express these restrictions as a population moment inequality. And given a fixed candidate menu, we can determine the admissible subset. These are the ones that meet all of the moment restrictions. This is a population object. It encodes conceptual uncertainty, separate from sampling uncertainty that comes from estimating it. For each candidate measure, we also want to report slack in the restrictions because we want to understand which restrictions drive admissibility. Are there certain restrictions that are really important in determining if this measure is valid or not? Would conclusions change if we used alternative thresholds, which hopefully are kind of are supported by benchmarks, prior evidence, et cetera? Are conclusions robust or do they appear relatively fragile? What we ultimately care about is some construct identified set, such as a regression coefficient, a treatment effect, a structural parameter. And given this, we can define the set of target estimates that we obtain through taking the admissible measures and using them in our downstream analysis. If we have a scalar target, our goal is to estimate a confidence region. So we are interested in the impact of economic policy uncertainty on employment, and we have different measures of economic policy uncertainty that are consistent with our moment conditions. And now we want to say, well, how much does the regression coefficient of interest change if we use these different measures that are consistent with the theory? And so there's uncertainty in beta hat for each candidate measure, and there's also uncertainty in the estimated moment inequalities that determine which measures are admissible, which measures are consistent with theory. And these can be coupled. We're not going to talk about estimation today, but existing partial identification and endpoint inference methods can be combined to estimate a valid, if conservative, confidence region. As I said, this is an important, question. And I think it's something that I'd like to encourage more research on. Hopefully there will be a package soon that automates this and makes thinking about this a bit easier, but I think that there's also a lot of scope for methodological advancements, and I think with AI, we just can't avoid this question. All right. And so I'm going to go ahead now and move away from construct validity and talk about observational validity, which is quite a contrast because the literature is actually really well developed for observational validity. Okay, so again, to recap what I mean by observation, with observation, you already have a specified construct and you want to take that and implement that at scale. Deep neural networks are the state-of-the-art tool for large-scale feature extraction from unstructured high-dimensional data and are increasingly being used by economists, by individual researchers to construct data on a large scale for empirical research. Importantly, though, we cannot assume that neural networks will generically produce unbiased predictions in finite samples. Systematic biases can arise from the network architecture, the distribution of the training data, other implementation details. We're taking nonlinear transformations in the neural network. We're applying it to binary and multi-class classification. This all violates classical measurement error assumptions. And so to the extent that the AI makes mistakes, and if you use AI, you see that it always says at the bottom of the screen it may make mistakes, and indeed it does, we can't assume that those are classical. And so typically, we oftentimes think of structured data as proxies. And this is what was feasible to do historically. It was very costly to create data by hand, and oftentimes you had to make do with some existing measure that existed. But in a world of inexpensive AI, such as commercial large language models, if we treat observation as the construction of proxies, this poses quite serious challenges for the integrity of empirical work. Okay, so the first challenge is that choosing different models, different training data distributions, different implementation details that are unrelated to the construct definition itself can produce different predictions. Indeed, this happens, and it can lead to bias. It can make it difficult to interpret the results, and it leads to post-selection inference concerns. We could try to address this with sensitivity checks, but as I argued in the last lecture, they're not going to fully address this concern because biases can be systematically correlated across models. Moreover, economists frequently use proprietary large language models, proprietary neural networks, and this raises reproducibility concerns. So suppose you use Opus 4.8 for your paper, but by the time the paper is published, years later, that has long since been deprecated, and you go to use kind of the most recent model, and you get a different answer. That's a problem. But at the same time, these models are so powerful, like we wouldn't want to not use them because of that issue. And then finally, it's typically possible to improve neural network predictions given you have a well-defined kind of objective through costly investments. You could, train on more data, train on better data for longer, have a customized model instead of using something off the shelf. But it's unclear how to assess which investments are worthwhile if you don't have a principled way to account for how prediction errors from your neural network affect the estimation of whatever parameters are of interest for your research question. So in order to address these challenges, it requires a shift in perspective, moving from informally choosing proxies that are plausible to, first of all, specifying the measurement aim. In other words, we need a well-defined construct, and then validating observation. How well is that aim defined and implemented at scale? And so statistically, what we would like to have is a broadly applicable framework that can correct the biases in observation that come from imputing data with a neural network. Yielding target parameters that are robust to the choice of measurement instrument. So what does that mean? It means, that if I use Opus, if I use GPT 5.4, if I use an open source model, I will get, up to error, statistical error, I will get the same answer. And we would also like better measurements to improve precision, which clarifies the cost-benefit trade-off of making investments in better measurement. Unfortunately, just such a framework exists, and it's existed for 50 years, more or less, which is the missing at random mechanism by Rubin. And so you might be saying, I thought we were talking about inference with AI predictions. Why are you talking about missing data? Well, observation, inference with AI predictions, right, is framed in this way because we typically lack the low-dimensional summaries needed for statistical analyses when we're using high-dimensional unstructured data. So you have millions of newspaper articles. Those newspaper articles do not come with a label that says, this newspaper article discusses economic policy uncertainty, yes or no. That's missing data that you need to impute. And so that's why this is a missing data problem. And it turns out that once we frame inference with unstructured data as inference with missing structured data, there's a whole kind of large literatures, a whole range of tools that we can apply. And in particular today, I'm going to talk about a framework called Missing at Random Structured Data. This is joint work with Jake Carlson, who's an econometrician. He's on the job market this year and doing lots of fantastic work kind of in this space of AI and inference. And this tries to make kind of a long-standing literature applicable to applied economics. Okay, so the core idea of missing data problems is that we're going to use a validation sample to estimate the bias in the imputed structured data and adjust our estimates accordingly. Validation data come from some implementable construct definition that's specified by the researcher and treated as given. It may be a silly way to measure that, particular concept, but it's stated explicitly, it's taken as given, and you take that construct and you apply it through some non-scalable process. That could be everything ranging from, ground station temperature measurements in the case of remote sensing data to export annotations in the case of text. I have a rubric for economic policy uncertainty. Does this article discuss it? Yes or no? And the key assumption in these frameworks is missing at random. And so what that says is after adjusting for observables, your annotated and unannotated data are comparable in their ground truth values. What do I mean when I use the term ground truth? Importantly, I'm using that in the machine learning sense. It doesn't mean fundamental truth. Remember, the goal of measurement is not to uncover some fundamental truth. Instead, it just means the label that it would have if you applied your kind of well-stated criteria to that particular observation. This means that there's no unaccounted confounders that determine whether an instance of unstructured data is annotated or not. Okay, so semi-parametric inference lets the data speak for itself as much as possible. And why is this so useful when we're doing inference with AI predictions? Well, the missing at random assumption makes minimal assumptions about the neural network itself. And so by having missing at random, we don't have to make strong assumptions about the neural network and how its biases shift, which we don't want to do because they shift in really complex ways with the inputs, with kind of what sort of unstructured data we feed into them. And as has already been referenced several times, people have difficulty predicting how this domain shift affects performance. And so if we can avoid it, we really, really don't want to have to make an assumption of like, this model with satellite data was estimated in the United States, and when we go and estimate, how it predicts crop type in South Sudan instead, the errors are going to be the same, right? Because we would expect the biases to shift in complex ways, and there's a large literature that shows that they do. And so by assuming kind of missing at random, we're able to make minimal assumptions about the neural network. Of course, if we don't have missing at random, you're going to have to impose stronger restrictions, and that's what the final lecture is going to be about, because of course it's not always feasible to impose this missing at random assumption on the annotated data. Okay, so this idea of debiasing, kind of essentially collecting a validation sample and adjusting for the measurement error is not a new idea. Okay, there's large literatures on measurement error, semi-parametric missing data, causal inference, valid inference with black box AI predictions. Actually, this problem is very closely related to causal inference because causal inference is also a missing data problem where it's your counterfactual treatment outcomes that are missing. And so the idea of debiasing is not new. It's very well established. What the MARS framework does is to try to make this as accessible as possible to applied economists who are working with AI predictions. We try to unify insights from these literatures into one applied framework, identify estimators that are both unbiased and efficient, and finally extend debiasing to common settings with limited guidance, including aggregated missing data. And we do have an R package that will allow you to produce all the estimates that you'll see me present today. And so hopefully it makes it straightforward for people to use this. All right. I want to give a motivating example. This comes from Baker, Bloom, and Davis in their paper on measuring economic policy uncertainty. I choose this example because it's one of the most influential papers on text analysis in economics, one of the most cited papers in economics over the past decade. And so their measure of economic policy uncertainty computes the share of articles in a set of newspapers that also satisfy a keyword query that indicates that this newspaper article is about economic policy uncertainty. And they perform an audit study that collects extensive ground truths on mentions of economic policy uncertainty in a randomly selected set of newspaper articles, right? And so that's another reason we chose this. Very few papers have really extensive validation data. This paper does. And so what I'm going to show you is the original and debiased EPU indices, where the debiased indices are adjusting kind of the predictions from the text analysis towards what we see in their validation data. And I'm going to do that both for their original keyword classifier, and I'm going to apply AI to this problem, trained on their labeled data. And so you can see what this looks like kind of with modern text analysis. And so we're going to take 25% of their validation sample and use that for debiasing. So this is the sample where we have both the predictions, either of the keyword classifier or the AI. And then we're going to use the remainder of their data to train a large language model to be able to make these predictions. Okay, so they're taking tens of thousands of newspaper articles, and for each year in their sample, they're constructing the share of newspaper articles that discuss economic policy uncertainty. And so you can see, their original measure is the pink one. They're using keywords. We can use a neural network. And you see it looks not identical, but kind of fairly similar. And then we have the debiased version of both the neural network, which is the one labeled long form or the green, and the keywords. And there's a few things to highlight here. So the debiased estimates have larger confidence intervals, right? Because they're taking into account the uncertainty that comes from the mistakes and the text analysis, kind of relative to the ground truth created by the authors. And the worse the model is, the wider those confidence intervals are. So the keywords aren't as good as the large language model. And so once you adjust for the uncertainty that comes from the prediction error, those are the widest confidence intervals. If we had an even larger set of training data, I think we could kind of shrink the confidence intervals and the green estimates from the large language model down further. In the extreme, if you had kind of a perfectly predicted model, those confidence intervals would look just like the ones where you ignore that these are generated kind of by a language model and just take it as the truth, which is what the blue and the pink do. Okay, and you see a little bit of downward bias kind of relative to their ground truth, but it's not huge. And we wouldn't expect it to be huge given how much emphasis this paper put on validation and how widely cited it is. All right, so that's a motivating example. I'm going to show you how those intervals are constructed. I do want to acknowledge that there is a very large literature on debiasing. I'm not going to have time to explain what all these different frameworks do. Some of these are from statistics. And essentially here we have different things that your framework may be able to do. What type of estimates is it? What are the assumptions? Does it allow for an unknown pi, which is the function with which data is annotated? So if you didn't know how the data was annotated, you might not know what that is. You might have to estimate it. Does the framework allow for that? Does it allow annotation to be non-uniform, so you don't just have a simple random sample, which is important. Often a simple random sample will not be sufficient. Does it worry about efficiency? Does it allow for fine-tuning, sample splitting? Does it allow for high-dimensional features, so unstructured data at all? And importantly, does it allow for aggregation, which is a point I'll return to in a few minutes, and is one of the things that motivated me to work on this framework. Essentially, at least in the sort of economics I consume, I'd say 99% of the time, you're taking predictions from AI models and you're aggregating them. The economic policy uncertainty predictions is at the level of the newspaper article, and you're aggregating that up to economic policy uncertainty in the US in 1997, and then taking a log and interacting it with firm level exposure. You're doing all kinds of things to it. And these frameworks, kind of existing frameworks, don't allow for that. They require you to kind of have validation data at the level of your parameter of interest. And so essentially the summary here is lots of these pieces existed before, but we're putting them together into one framework so that you don't have to go read a bunch of different papers. It's all in one place. All right, and so I'm going to introduce that framework now. So we're going to start with structured data, which we refer to as M. These are low-dimensional data that can be used directly in estimating equations, but we don't have them initially. All we have is the unstructured data, the text, the images. They're high-dimensional, and we can't use them in our analyses. And those structured data are missing, and so we need to impute them. And so we're going to impute them with some function mu hat. Because we have this criterion-based measurement that we can use for annotation, like that could be me sitting there looking at the newspaper article and saying, does it, given this criteria, does it match? Is this about economic policy uncertainty? I can't label 100 million newspaper articles, but a neural network can do that pretty easily. And so we're going to have the scalable technology mu hat that allows the researcher to leverage the full kind of unstructured data set, which might be on a massive scale, but it's a black box. And deep neural networks are increasingly serving as the imputation function. Okay, so we're going to use potential outcomes notation. Not surprisingly, as I said, this missing data problem is closely related to the Rubin causal model, which is itself a missing data problem. And so we have our structured data M, and we have the ground truth. That's just what comes from applying your rubric. That's M star, and we observe that if A, which is the annotation indicator, equals 1. And so we're going to need some assumptions for this framework. You're going to see that they're very similar to the causal inference assumptions because, again, they're both missing data problems. So we need consistency of potential outcomes. All that means is that annotation status is well defined, which will tend to hold trivially, and that the label for any given kind of piece of any given instance, so any given text, image, etc., depends only on its own annotation status, not on the annotation status of other observations. You can do that by having a well-defined rubric, right? That should help with that assumption. The key assumption is missing at random. After adjusting for observables, which we denote here by X, the annotated data and the unannotated data are comparable in their ground truth values and the values that you would get by applying the rubric. And so this is just analogous to selection on observables and causal inference. It's essentially the same assumption. You could call this annotation on observables. The third assumption is that we have a known and bounded annotation score function. This annotation score function pi is our decision rule for deciding which instances we're going to label. This embeds the assumption of strong overlap, often seen in observational causal inference settings. So we're not putting zero probability on annotating certain types of text or images. We're going to assume in the baseline it's known. And it will be, if you're the one who annotated the data, you know how you did it. Okay, so this is pretty weak, but we can relax it for settings where it's not known. I do want to make a note that some people say, like, I don't like this assumption of strong overlap in this setting because let's say you have 1 billion texts. I mean, realistically, you can never annotate more than a vanishingly small fraction of them if you have truly big data. And one of the kind of advantages of seeing that this is analogous to the causal inference setting is that there's a causal inference literature on decaying overlap, and from that we can see that nothing would kind of fundamentally change if we allowed the number of annotations to be diverging, but the ratio of labeled data to unlabeled data to converge to 0, right? So even if you're in the world where you have 1 billion things and you can never label more than a small share of them, you should be okay. The size of the labeled data is going to be important. I'll just make that as an aside. The final assumption, which we only need if we care about efficiency, we don't need this to be unbiased, is that we want the expected square error of our estimator to go to 0 as the amount of data we train the estimator with goes to infinity. And this is very weak in the context of neural networks like transformers. But again, you don't need this assumption for efficiency, right? You could use a model off the shelf. It's not doing anything asymptotically because it's fixed, and you're fine. Estimates will still be unbiased, even if the efficient thing to do would be to train a model to get it to be as accurate as possible. Now, if the annotation score function is estimated, so you're not the one who labeled the data, you have to estimate how somebody else did it, then you need to make assumptions about the rate of convergence. But we're not going to worry about that for now, and I think they're reasonable. Okay, I want to spend kind of the remaining time discussing common empirical scenarios. And again, everything that I'm going to show you, there is an R package for, which is linked at the end of the slides. Okay, so first of all, I want to talk about how do we identify a mean with missing data. So we've ran the language model over the newspaper articles, and we want to know mean economic policy uncertainty in each year, like in the figure I showed you. So in all of this, we're going to follow Chin et al. 2008, who provides general results on semi-parametric efficient estimation for parameters identified by moment conditions with missing data. And so we can put everything into her framework, and it kind of makes things the most straightforward. And so we can derive an expression for that mean, which some of you will recognize as an AIPW estimator. For others, this might look, just like a bunch of confusing math. And so I want to go to the next slide and break this down a little bit. So remember, we're trying to estimate a mean from predictions from an AI model. And so we can break this expression down into two terms. The first term, A, is just the mean from your AI predictions. This is what you would get if you just ignored the fact that you use AI to generate this data. So this is like kind of the blue and the pink estimates in the figure of economic policy uncertainty that I showed you. This second term, B, is essentially an estimate of the measurement error of the neural network in the annotated sample. And so, if your LLM makes perfect predictions, this term will be 0 and it will go away. On the other hand, if your LLM makes very poor predictions, this term is going to be very large. It's going to have a large variance and it's going to blow up your standard errors. But your estimate is going to be adjusted kind of back towards your annotated data, kind of weighting according to the probability that type of observation with those observables appears in the annotated data. We could write this a different way, where instead we think of it as the mean in the annotated data plus a non-parametric regression adjustment to adjust for systematic differences between our large unlabeled sample. So the first way of writing it appears in a large literature on black box AI. This way of writing it appears in a List et al. Paper, but they're two different ways of thinking about the same thing. Okay, if you understand mean estimation, you will understand every other estimator that I'm going to quickly show you. Essentially, in all of these, in our annotation sample, we're measuring the measurement error, and then we're adjusting our estimates accordingly. And that intuition carries through to many different examples. So we could do linear regression and think about the standard expression for an OLS coefficient, right? R prime R inverse R prime Y. That's what we have here, except the Y, which is our missing outcome. Now we're doing the same adjustment that we did for the mean, right? Where we're adjusting for the fact that our annotation data kind of differs systematically from the predictions from our AI model. And so you can think of this just as the standard OLS estimator, but the outcome has been replaced with what's sometimes called a pseudo outcome in this literature. One important thing to note here is that your imputation function should be a function of your context-specific variables. So like the controls in your OLS regression, if they are relevant for predicting the outcome, which is something I think that hasn't been emphasized in the literature. Okay, we can do linear regression with a missing regressor. This looks much messier, but it's still like the standard OLS regression coefficient estimator, but now adjusting for the fact that our regressor is missing. We can do IV. Let's say our outcome is missing. This is our standard TSLS estimator, but we're adjusting the outcome for the systematic differences between the imputation and our annotated data. Again, we can make the instrument missing. Looks a bit messier, but same thing. Standard TSLS, but adjusting for the missing outcome. We can do differences in conditional means. This is where differences in differences comes in, regression discontinuity, average treatment effects, and RCTs. And essentially, these are all just differences in conditional means. And so the estimator is just going to be a difference at kind of in the conditional mean, which is computed analogously to the mean example that I showed you. We can do the same thing with a conditioning variable. Again, it looks messier, but it's this, the standard estimator, but adjusting for these differences. And finally, we can do this much more generally. I know that this kind of looks much messier with the notation. And so I don't want you to worry too much about the expression, although this expression there, like it should look familiar, right? It's just a more general form of the expression we've seen for every one of these estimators in the just identified case. You can actually do the same thing in the over-identified case, although I won't talk about that today. There's two conclusions that come out of this that are important. So first of all, this has a type of double robustness property. What I mean by double robustness is we can use kind of any imputation function we want. You could apply AI in the stupidest way possible, be super noisy. Your confidence intervals would be massive, but they would still be valid when you do the debiasing. And the second thing I want to emphasize is that the efficiency implications of this are it seems obvious, but this is what comes out of the proofs as well, is that you want to learn that imputation function as well as you can. You want your neural network to be as accurate as possible, and that will give you kind of the most efficient estimates. All right, aggregation. As I emphasized a few minutes ago, the bedrock assumption in this literature is that ground truth data are available for the imputed variables that are used in the estimating equation. This typically fails because we might take, say millions of individual social media posts or newspaper articles, aggregate them up to some aggregate level. We might transform them, like frequently we take a log, we might interact them with something, and then we run our regression, right? And that's really kind of what motivated me to think about this, because it's a mismatch between kind of all the existing work and what often applied economists need to do. And fortunately, the answer is really easy. So this is great news for all of us. And so we're going to kind of assume you want to run some regression, right? And it's on some kind of aggregation of your data that you've imputed with AI. And so think of this as mean economic policy uncertainty kind of transformed in some way. Well, what you can do is you estimate the aggregation using the Mars first step estimator. So in this case, using the mean estimator that I showed you. So we estimate mean economic policy uncertainty using that mean estimator. I showed you those estimates in the graph. And then we can plug that into our aggregated regression. Now, when we debias, does that mean we don't have measurement error anymore? No, it doesn't mean that. We still have measurement error, but what valid debiasing does is it takes systematic measurement error and turns it into classical measurement error. And so our estimate of mean economic policy uncertainty in the US in 1997 still has measurement error, but because we've used the Mars framework to debias that, now that measurement error is classical. And then we can just proceed kind of with the standard adjustments for classical measurement error. You can do that in Stata. People have been doing this for decades. It's all very straightforward. Sometimes people don't like adjusting for classical measurement error because they say the variance of the measurement error, do we really know that? Well, the situation where it's plausible that we know that is that when we have a really large sample, and in the big data world, that's precisely where we are. And so I think it's kind of plausible to do this adjustment. And it's because it's classical measurement error, we know how to address it. So we can extend it to clustering, to panel data, to heterogeneity and the variance, to kind of all types of different things, right? And so it makes the problem relatively straightforward. But what is essential is that when we compute that aggregate measure, we're going to debias. And at that level, we do have the validation data to create that mean or whatever function kind of we're taking of the kind of individual level predictions to aggregate up, those newspaper article predictions into something that is for the US in 2002. And so we can do this for Baker, Bloom, and Davis. They're going to look at how the change in employment relates to the change in log economic policy uncertainty interacted with firm year policy exposure, plus some additional controls, et cetera. And this is what we get. So on the right-hand side, the blue and the green are kind of the estimates ignoring that we have imputed anything, with the keywords and with the LLM. If we take, on the other hand, we debias to compute mean economic policy uncertainty, but we ignore the classical measurement error problems, we get the gray and the pink that are on the right. So that's, again, with the keywords and with the LLM. And then finally, we can adjust for classical measurement error on the left. It's blowing up the standard errors. Part of this is because they're taking the difference in economic policy uncertainty, which makes the classical measurement error correlated across periods. But in general, in this case, the conclusions are actually pretty similar. If we had a slightly more accurate neural network, which I think we could with more training data, we would get the same kind of statistically significant result. But this is not the paper I'm worried about that I reproduced because they had really, really extensive validation data and were really careful to try to measure things accurately according to their construct. I'm more concerned in cases where people aren't doing that, that we need a form of validation. Okay, so I'm running short on time. I'll just say that, in the paper, we talk about how do you annotate data in practice. Okay, but I'm going to kind of skip through this because I'm short on time today. You can do a power analysis. How many labels do you need? The important thing is that in practice, we find oftentimes you don't need that many. If what you're trying to predict is a binary indicator, oftentimes a few hundred labels is enough. Okay, so this is not something that's prohibitive in terms of the amount of time it takes you. Hopefully all the time that you're able to save by maybe having coding agents help you run your regressions should be plenty of time to be able to do some validation. All right. Having more annotated data is good, but the most important thing is having a more accurate model for your standard errors. So in conclusion, deep learning provides powerful tools for measurement. Accounting for imputation bias avoids many challenges that arise with imputing when we just treat things as proxies. And we have a package to hopefully make this easy for everybody to implement. But of course, this framework does not apply to everything. It applies to many common empirical scenarios. But notably, what happens if the missing at random assumption is impossible to satisfy? And that's what the final lecture is going to treat. Thank you.
Okay, awesome. We're almost there. It's like after 5. I'm getting sleepy myself. But there's a ton of material here. This would be stuff that we would probably cover over several months in a PhD course. So slides are online, tons of references, lots of resources. Please reach out if you have questions. So the last 40 minutes or so, I want to talk about what happens if we find ourselves outside of the case that Melissa was just discussing at length. And so let me just sort of talk a little bit briefly about how I think about this validation sample framework at a very high level. So, in a lot of settings, we as researchers, we're going to collect some unstructured data, documents, images, videos, and link them to some covariates. And the reason we're interested in this unstructured data is we think that it expresses some construct that we're interested in studying. And that construct might be defined by an existing measurement process that in my slides I'm going to denote by F star. And then we would like to report some downstream parameters that are defined over the joint distribution of VI star and WI. This measurement process is something that the researcher has to choose themselves. And I think of it as what the researcher would use if they were truly unconstrained in terms of time and resources. So in text analysis, oftentimes that looks like, well, we would like to write a very careful and extensive rubric that defines the construct and adjudicates edge cases. And then in an ideal scenario, we would have experts or a team of experts label each document in light of this rubric, often in short sessions to prevent fatigue from introducing error. Or in environmental/development economics, perhaps the ground truth, the best case measurement process is that we would send surveyors into remote forests at high frequency to measure tree cover. We would send surveyors out to remote villages in order to ask people extensive consumption surveys. Or we would blanket physical fields with actual monitors in order to measure pollution. Now, the core problem we face in doing this sort of research is there's a measurement bottleneck here. Applying our existing measurement process across the full sample is just infeasible. We could not have a team of experts, get a bunch of macroeconomists in the room to carefully read every single newspaper article that has been published over several decades. For cost reasons, we can't send surveyors into remote forests at very high frequencies or blanket fields in our experiment with physical monitors. So this existing framework on using validation data asks the question, well, how could we use machine learning or AI-generated measurements that I'm going to denote by RI to solve this measurement bottleneck? And as Melissa, really nicely explained, the solution so far is the following. Let's collect our machine learning or AI-generated measurement on our full sample of interest. On a random validation sample, let's collect the existing measurement we would like to study, and let's use that validation sample to debias the machine learning or AI-generated measurements. And this is really a beautiful idea. It's built on a lot of old ideas in measurement error and survey sampling, and it's been really recently resuscitated in a lot of work at the intersection of machine learning and AI. And Melissa's paper with Jacob is a great introduction to the ideas in this literature. Now, why is this solution so attractive? The reason this solution is very attractive is that frontier machine learning and AI models are extraordinarily complicated. If we think about a language model, that's billions and billions of parameters trained on data that you have never seen nor will ever touch. And those models can make errors. So we would like to correct for measurement error in their outputs without having to make strong assumptions about properties of these outputs. And this is a framework that allows us to do that. So the payoff of having validation samples is that we can recover the estimand that we're interested in, which is defined over the joint distribution of V star and WI, while only paying measurement costs on a subset of our sample, on the random validation sample. Of course, to execute this framework, there are two requirements here. The first is the researcher must choose an existing measurement that they would like to scale over their sample. They have to define this object F star. And the second is that the validation sample must be collected from the researcher's population of interest. So what I want to talk about in this lecture is, what happens when these two requirements fail? In the first case, what happens if there is no existing measurement process that we would like to scale? I think in going over the last couple of years and presenting these ideas, people push back and make this argument most often in text applications where they would like to label documents with large language models. So I'm going to illustrate this idea in that setting. And the second is going to be one in which there is in fact an existing measurement that we care about and would like to defend, but it exists in some other sample. And this most often arises in applications involving remote sensing with satellite imagery or digital trace data, where there is existing measurements from surveys that we may have run or existing censuses that cover another region or period than the one that we're studying at hand. So in both of these points, there are going to be just some key ideas I want you to take away. And there's going to be some details. Don't worry about if they go too fast. Slides will be available. But the first one is if there is no existing measurement that we'd like to scale, we're going to have to fall back and start introducing assumptions about measurement error. And what I want you to keep in mind is that when we start making assumptions about measurement error in these settings, we're really making assumptions about the behavior of frontier AI models. So I'm going to illustrate that in the context of one example where the construct that we're interested in studying is latent, but we might want to treat ML or AI as offering us many repeated measurements of that latent construct. And then I want to revisit some classical identification results from the measurement error literature using what we know about frontier model behavior in computer science and AI. In the second case, when there is an existing measurement we care about, but it exists in another sample, we're going to face a data combination problem. And what I want you to take away is that identification is going to turn on what you're willing to believe is stable between your sample and the auxiliary sample where you have the existing measurement and the AI output. And what I want to point out is that two very natural assumptions we could write down here, both work quite well if they are true, are actually going to be incompatible with each other outside of knife edge cases. So this is going to be a place where you'll really have to pick an assumption and try to defend it. And we'll talk about how you might approach that problem. So let's think about this first case where we worry that there may not be an existing measurement we care about. So again, I want to think about this in the context of text, where the measurement process, the best case scenario, typically proceeds in two steps. Step one, as Melissa was articulating, is one of definition. We, the research team, would want to draft a very detailed rubric for the construct that tries to adjudicate edge cases and surface edge cases, possible disagreements, and iterate until we're satisfied we have worked out the kinks. Then in step two, we'll take that rubric and train annotators, ideally experts in the domain, to apply that rubric across the corpus. So what the solution Melissa presented so far would say is to incorporate machine learning and AI into this process. Let's invest in step one, create a detailed rubric that we would care about, then only run step two on a random subsample. If we do this appropriately, we can still recover the estimand defined by V star. Now, I think a question definitely in my mind, maybe lurking in the back of your mind, is in 2026, why should we privilege trained human annotators once the rubric is defined? After all, in 2023, GPT 3.5 was already able to ace the GRE. Last summer, it was getting a gold medal in the IMO. And it seems like every single month there is a new model. And if you're on Twitter, you're seeing impressive benchmarks about them. So if frontier AI can accomplish these feats, why are we trying to privilege human annotators in this process once we have defined the rubric? So I want to now grant that point for a second. And let's just imagine we took the rubric we wrote down and just presented it to frontier models rather than trained annotators. And what it's important to keep in mind is that, as Melissa was articulating, the rubric alone does not pin down the measurement that's going to be produced, say, by a frontier language model. There are many choices that the researcher still has to make. First, what model do I use? Do I go to the OpenAI family? Do I go to the Anthropic family? Do I go to Gemini? Do I go to DeepSeek or some open source model? And then even when I've committed to a model, there's a question of what's the prompt engineering strategy going to look like? What's going to go into the system prompt? What's going to go into the user prompt? And if you go to your friends in CS, there is a whole literature trying to talk about different prompt engineering strategies to improve behavior. So it begs the question, do these additional auxiliary choices change the resulting measurements? And this is not even bringing into the fold, there is additional variation that arises from inherent randomness in model outputs and changes in model releases that are often hidden to users. And some of the data editors at economics journals actually put out an article last week flagging those concerns as well. So I want to illustrate what happens. So I'm going to take a data set of congressional bills through 2018, about 10,000 of them that we randomly sampled. And for each bill, we have a text description of it. We can also link that bill to the party affiliation of the sponsor of the bill. The DW nominates a sort of measure of their partisan valence of the sponsor of the bill and whether the bill originated in the House or the Senate. And some political scientists actually went through the very painful process of writing down an extensive rubric, training a team of annotators for an entire semester. It's a really heroic effort to go and label all of the bills in Congress for their policy area. Is this a bill about defense spending, health spending, et cetera, based on the text description? So for example, this could be a bill to revise the boundary of Crater Lake National Park in Oregon. Then what we did in some work with Jens Ludwig and Sendham Malai did is we said, well, let's take their rubric and let's use various prompt engineering strategies from different models in OpenAI's GPT family to label each bill's policy area. And then let's just run a bunch of regressions where we're going to plug in the language model label on the left-hand side and then regress it on a bunch of these other economic covariates and just see what happens. If you do this, what you get is that across models and prompts, your estimates can wildly vary, both in terms of magnitude, significance, and even sign. Different models produce widely different estimates, and it wasn't obvious to us, ex ante, we first did this in 2024, whether there would be improvements as models improved. So a year later, we revisited it with GPT-5 and the problem. Let me do this in another example. There's a really wonderful piece of computational social science that studies speeches on immigration in the US Congress over about 140 years. And what they wanted to do is they wanted to take each speech, they observe the text, they observe who was the speaker of this speech, what chamber they were speaking in, and within the Senate or Congress, and also their partisan affiliation. And what they would like to do is they want to take this to the text of that speech and label it. If this is a speech about immigration, is the speaker speaking about immigration in a pro-immigration manner, in a neutral manner, or in an anti-immigration manner, and then see how that correlates with partisan identity over time. So, you could now revisit this exercise in 2026, use various prompt engineering strategies, take the rubric they wrote down, now incorporating models from OpenAI's family, Anthropic's family, Gemini as well, to label the tone of each speech segment. And then again, just plug those in on the left-hand side and see what happens. And again, you see that across models and prompts, the estimated partisan tone gap differs enormously in magnitude and in sign. So, what's the point? Given the rubric, there are still many important choices that an empirical researcher would have to make, which model, which prompt, and those choices, seemingly innocuous to us, can really move estimates in magnitude, significance, and even sign, and there's a lot of work documenting this fact across computational social science. So you could look at this variation and have one answer, well, why am I treating the model as a proxy? Let's stop doing that. The construct we're interested in is the model's output. The measurement process is then going to be defined by a particular model under a particular prompt. I think that's a complicated route you could go down because now then the estimand is going to be indexed by the choice of model and prompt. Our researchers using different models and prompts really studying different estimands. How are we as a field supposed to manage the choice of GPT, Claude versus Gemini, the choice of prompt? Are we supposed to revisit empirical work every single time a new frontier model releases? I think that's a set of challenging questions you would have to answer if you wanted to go down this path. Now, let me just flag, there's been really interesting work over the last year where researchers are trying to build better harnesses, sort of the environment in which a language model sits, to try to make them more robust to different prompt engineering strategy. This is the only example I know of people trying to do this at scale, and so this is an important avenue for us to try to really invest in. How would we build harnesses to reduce sensitivity? But let me just bracket that off for now. So we're not going to be thinking of defining the construct as the model, but again, maybe we still think there's not an existing measurement that we have access to. So what would be an alternative view we could try to go down? An alternative view we could try to go down would be to say, look, the construct we're studying is something that's inherently latent. There is no feasible measurement process that could recover it, whether human or machine. Every single label we generate, whether by human, RA, expert, or AI, is just an imperfect proxy for this construct of interest. So if you took this view seriously and then went back to your econometrics classes, you'd say, well, this sounds a lot like saying that we have potentially many repeated measurements of this same latent construct, even though we never directly observe it. So could we then try to take classic ideas from the measurement error literature to make progress? So let's just do a reminder of what would be one classical identification strategy from the measurement error literature. So now I'm going to let little k index different model and prompt combinations where RIK is going to be the measurement generated by that particular model prompt combination. And let's imagine this construct we're interested is binary, just 0, 1. And the thing I want to learn about is just its base rate. How often is the construct equal to 1? So the key assumption in a lot of this work is going to be to assume that if I were to condition on this latent construct, then these measurements are independent of each other. If I was in a classical measurement world, I have two measurements that are independent of each other. I could use one as an instrument for another. That idea really generalizes. And in particular, the intuition you can have in the back of your mind, but you could spend time and prove it more carefully, is that if I was willing to make this assumption, what I get to learn from the data are 2 to the k minus 1 probabilities. There are 2 to the k plus 1 unknowns that I'm trying to infer. And as long as k is bigger than or equal to 3, I have enough equations relative to unknowns so that maybe I could solve this problem. And indeed, that intuition's right if you're willing to make some auxiliary assumptions. And in particular, those auxiliary assumptions would be that these measurements are informative about the latent construct of interest, meaning the probability of a true positive is larger than the probability of a false positive. And you can generalize this in a lot of ways. There's a lot of fantastic work in measurement error trying to take this idea and run with it as far as you can. So what if we tried to take this idea to large language models? Well, now if we take this idea to large language models, the measurement error assumptions we're writing down are properties of measurements. Here, the measurements are outputs of large language models. So we're really writing down assumptions about the behavior of frontier AI. So we have to ask ourselves the question, which of these assumptions are credible? So in this simple case, the additional informativeness assumption feels very mild. Presumably, if you were a researcher willing to use a language model to produce measurements of some construct, you probably were willing to believe this up front. The problem is going to come in this conditional independence assumption. Is that really going to be credible for large language models? It would say that co-movements in the outputs produced by these language models, different prompts, is only going to be driven by this latent construct. Errors, therefore, must be unrelated across models and prompts, conditional on the latent construct. Why might we worry about this? Of course, there is substantial overlap across frontier AI labs. There is substantial overlap in the sorts of data they pre-train on. There may be differences in what is the data they use for fine-tuning on human feedback, fine-tuning on verifiable rewards, but they're presumably drawing those from similar domains. And also there are shared architectures across these models as well. And this is not just something that we're worried about. There's a very active literature in computer science under the lens of algorithmic monoculture that tries to think about this problem more seriously. But ultimately, we can talk about this and why we might be worried. This is ultimately an empirical question about the behavior of these models. And where do we understand or how do we learn about the behavior of these models in practice? So if you are too online, like myself, you've probably seen every time a new language model is released, widespread publicity around benchmark evaluations. The real quantitative basis of our understanding about model performance comes from benchmarks. And you can think of these as looking at the performance of 3 years ago, GPT 3.5 on standardized exams. The people then moved to more domain-specific exams. As those got saturated, we moved to benchmarks that try to test more general intelligence or coding benchmarks, math problems, et cetera. So in other words, we evaluate performance by asking these models questions and evaluating the outputs. So we could try to do this to understand this measurement error assumption. Rather than just talking about why errors might be correlated, let's actually go and look. So as I mentioned, there's this active literature in computer science under the umbrella of algorithmic monoculture, and they went and did this exercise on existing benchmarks used to evaluate frontier AI. It's a really wonderful paper by Nikhil Garg, who is at Cornell in his lab. So what did they do? Is they looked across pairs of models on different benchmarks, and then they reported how often 2 models gave the same wrong answer, conditional on being wrong. And they did this across a large set of models that are publicly available on Hugging Face, and then a large set of benchmarks that are publicly available as well. And what they found is that the wrong answer agreement across different models and prompts far exceeds what you would expect from random chance. And what's even more interesting is that this correlated errors problem is more problematic and more common on better performing models. It seems like with new model releases, outputs are becoming more and more correlated. And if you go to the paper, they have some really wonderful little heat maps that you can kind of stare at and try to understand and look at the correlation structure. But the point is, it's not blue. There's a lot of yellow here. Things are very correlated. But again, you may be skeptical and say, look, I don't care. This is evidence about AI benchmarks. We're talking about economics. What about the measurement problems that we as economists are interested in studying? So let's now revisit two running examples and assess whether measurements from different models and prompts are in fact conditionally independent. So let's go to this congressional legislation example. Let's go to this data set on immigration speeches in Congress and ask, conditional on what the authors treated as their existing measurement, would model errors be correlated with each other? So you can implement that in a more precise way. Let's generate labels from a bunch of different model and prompt combinations for each pair of model and prompt combinations. Let's calculate their joint distribution and compare that to what we would expect to see if in fact they were independent, conditional on the construct. And then we can summarize that in a test statistic and an associated critical value. So what I'm just going to show you next is what is the ratio of the observed test statistic relative to its 95% critical value, which is just a simple summary of getting a sense of how strong is the evidence against things being independent of each other, conditional on the construct. And what you find is, in the congressional legislation example, if you look within a model across different prompts, perhaps unsurprisingly, each prompt pair looks to be significantly correlated conditional on the ground truth. That's not surprising. This is the same model prompted in a different way. We would expect there probably to be a lot of correlation. If you do the same thing in the immigration speeches, you find the same pattern. But interestingly, on trying to label sentiment about immigration speeches, there's more correlation conditional on the ground truth and errors across language models and across prompts within a model. And then you can also do this across different models. So now each different row is a different model, whether GPT or Anthropic. And interestingly, again, you see while there is less correlation across model families, things are still severely correlated in general. So what is the takeaway? On benchmarks and in economic applications, it appears that errors are strongly correlated across models and prompts. So if we were to go to the measurement error literature and said, well, let me take this idea, let me treat language model labels across models and prompts as if they are conditionally independent, that would not be credible. So identification results that rely on it really should not be naively applied to LLM-generated measurements. But at the same time, that seems like a very pessimistic take away from this problem. The errors are correlated, but they're not arbitrarily correlated either. We saw differences when we looked across models as opposed to across prompts within a model. Taking a step back, to me, the cleanest framework for trying to incorporate AI outputs into empirical research remains through the validation sample. But I think that framework is often misunderstood. Properly understood, you should think of this as its goal is to try to automate and scale our measurements at our best. And best is not the compromise we settled with before AI. It's the measurement process you would actually defend, which is a documented, adjudicated rubric decided upon and applied by you, the researcher, not the undergrad RA that you were able to cheaply hire. And the reason for that, the reason why this framework is powerful, is that our best measurements no longer have to cover the entire corpus. A small expert-labeled sample may be affordable, and now you can use AI to scale that measurement across the corpus of interest. So in other words, and just coming back to a point that Melissa emphasized, really what we now have in the age of AI is that the scarce input for us is constructing high-quality measurements in the first place. And that's what we as researchers must be investing in. And as Melissa alluded to, we've been here before. When running regressions became cheap, the attention of econometrics, the attention of empirical research wasn't about how do I invert X prime X inverse. It became on how do we defend and find credible identification strategies out in the world and then let it rip from there. And a similar thing has to happen here. Invest in high quality measurements, let it rip with the validation sample framework. So the second takeaway is that once you step out of this framework, you're now in a world of making assumptions about measurement error. And making assumptions about measurement error are, in fact, making claims about the performance of AI and ML models. And this is a place where economics can do a lot of work and sort of take a step out of our comfort zone and start engaging with work in AI, where there's already an entire field that tries to study frontier model behavior through constructing benchmarks. And what I hopefully illustrated in that example was we have a huge literature in econometrics, that thinks about measurement error assumptions through these conditional independence. We could have assumed it ex ante, but if we went and checked it empirically, we'd find it falsified. But perhaps this exercise could provide some external calibration. And you can go to many long survey articles about deep ideas in measurement error and ask what would be the analogs of these strategies for AI models? How would we benchmark? How would we evaluate whether they're credible or not? And so I just want to end on a point that I think this section of the talk is that while there's a ton of work on benchmarking in CS, these are not the benchmarks that we as researchers need. They focus on the wrong tasks. They're thinking about math exams, coding, not measurement problems. And we're generally bad at generalizing performance to new problems. And furthermore, they often focus on the wrong properties, thinking about just overall accuracy, which can be a misleading guide to what is going to be the bias for downstream estimates. So developing and working on benchmarks for measurement in economics and the social sciences more generally is a really essential activity, one where we invest in constructing measurements and then asking how well do models reproduce, or how do they reproduce those. So far, what we tried to do here was to depart from this validation sample framework in one way, where we asked the question, suppose there is no existing measurement that we'd like to scale, and we talked about how measurement error assumptions are going to be claims about frontier model behavior, and benchmarks are how we could in principle discipline those assumptions. What I next want to talk about is another deviation from the validation sample framework, and that's going to be one in which we're not disputing the fact there is an existing measurement we would care about, but that measurement exists in some other sample. So one concrete idea you can have in the back of your mind would be ground truth. The object we're interested in is some consumption measure that we would collect if we got a household in some remote village to sit down for many, many hours and ask detailed questions about everything they ate in the last week. We like that as our measure of consumption. The problem is that was only collected in a census or a survey in some other region in some other time period. And this most often arises in remote sensing applications with satellite imagery or uses of digital trace data. So think about the trace data associated with cell phone usage. And in this case, the researcher is going to have to somehow combine the sample that they have of interest with this auxiliary sample, and identification is going to really turn on what is assumed to be stable across them. So in this case, the constraint for the researcher and what AI and ML may hope to alleviate is cost and coverage in collecting outcomes or covariates that we're interested in studying. There's been a ton of work about how unstructured data in the form of satellite imagery and digital traces, this mobile phone data, could help us scale existing measurements. And the reason being that satellite images, mobile phone data are collected at very high frequencies at very small granular geographic areas, and they're already collected by other companies, other space organizations. So how can we take advantage of these unstructured data to lower measurement costs? In experiments and observational studies, most often you see this in environment and development economics. So what are we going to think about? So again, researcher collects unstructured data, xi. Now you can think about that as satellite imagery or this digital trace data for each unit. Each unit is associated with some construct of interest, V star. Think of this as our survey measure or census measure of consumption, or perhaps some local environmental outcome. And then we may have access to a prediction, Ri, of this construct that is built from the unstructured data. So a prediction of local consumption from satellite imagery, a prediction of local pollution from satellite imagery as well. And there's been a lot of work, while this is a very popular empirical idea, there's been really wonderful work over the last 3 to 4 years documenting that while these remotely sensed predictions can be very accurate, they're still imperfect. There still is error, and there's error that's correlated across space and time. So you could take the ideas from Melissa's lecture and apply this again here. If you, the researcher, have a particular sample of locations in space, villages, collect your remotely sensed proxy on all observations, randomly pick a subset of villages or households to actually go and run the survey or collect the environmental measurement, and then again, go through anti-bias. But of course, collecting a validation sample, there's cost involved here. And oftentimes, the labels we care about can exist elsewhere. There may be a government environmental survey, a census from an earlier survey round, but those are often collected somewhere else. And so the idea would be, could we somehow use those, treat those like a validation sample, and I'll call them an auxiliary sample, where we observe ground truth, our predictions, and maybe additional covariates, but in the sample that we would like to run our experiment, in the sample we would like to run our observational study, we don't have that ground truth. We just have the remotely sensed prediction, covariates, and maybe some other treatments of interest. So can we use these existing labels to correct for the errors in RI? This is now fundamentally a data combination problem. So let me just push back on one thing you thought you could have. Well, I've heard ML, AI are really good at predicting. Maybe these predictions are going to perform well across time and space. If we had that view, what would we expect? Well, as I mentioned benchmarks earlier, there's a really wonderful recent paper by Jonathan Proctor and a team of folks in environmental and development economics, where they did the hard work of constructing a benchmark, where they said, let's take some pre-trained embeddings of satellite imagery called the Mosaics framework. That is itself a wonderful piece of computer science output. It is a publicly available API where anyone can go and pull embeddings of satellite imagery across the world. It's amazing, easy to use. And they said for about 115 socioeconomic and environmental variables, let's take this pre-trained embedding of satellite imagery, predict those variables using satellites, and then ask, how does the performance of those predictions vary across time and across space? And what you find is that as you move further and further away from the training sample in geography across every single class of outcomes they look at, there are large reductions in predicted performance. So if you're trying to merge samples across space, you should be worried about instability in the overall accuracy of predictions. You can run the same exercise. We can run the same exercises ourselves. I just wanted to do this in the lecture to illustrate how easy this is. This was about a week of work in collaboration with some Codex agents. Again, using stuff that you can all pull from publicly available APIs for Mosaics, and then there are other satellite embeddings as well called Alpha Earth. So just going to show you another example where we're going to try to predict an outcome index about living standards, which is a 14-component index of housing variables, infrastructure, assets, and financial access from the DHS survey. Train that on a bunch of geographic clusters in Kenya, and then ask how well the predictors are going to transfer to different parts of Kenya or Ethiopia or a different point in time. And then do the same thing to predict forest cover in Uganda, which is the setting where Seema Jayachandra and co-authors had a really wonderful early stage use of remote sensing in an experiment on deforestation. And again, what you find is if you try to transfer these predictors for Mosaics and then a more updated, a more recent satellite embeddings, Alpha Earth, you see a lot of transfer error, both across time and space. And that's true both for the living standards outcome and for the forest cover outcome. So we can't just take these objects and assume, on average they're going to predict as well. We're going to have to introduce some assumptions here. So let me just add a bit more notation in the last 5 minutes. Bear with me. We'll get through this together. So we're going to think about a researcher that has two samples. I'm going to call S equals E, their empirical sample. That's the sample where they're only going to observe W and the remotely sensed predictor, and an auxiliary sample where they're going to observe both the remotely sensed predictor and their existing measurement. So the target is going to be some parameter in an empirical sample, say the base rate of this outcome, or perhaps we have some treatment and we'd like to learn the treatment effect of D on this outcome of interest. How could we combine these two together? So one way we might try to approach this data combination problem is an assumption that I'm going to call here outcome stability, which at a high level, what is it saying? Is it's saying that our predictions of V star, given Ri and then possibly additional covariates, that prediction transfers across the sample. So conditional on seeing the same satellite image and having the same covariates, the distribution of the outcome of interest would be the same. If you believe that assumption, you could, take yourself back 1 year and you would find yourself in a framework that looks a lot like the surrogacy framework, and we could apply identification results from there to learn objects of interest in the empirical sample. And it's important to sort of think about what is this saying in terms of properties of the predictor. Outcome stability is again sort of saying that the predictor in machine learning has the same calibration curve in both samples. And I'm going to draw an analogy here to folks that are familiar with this literature. This is a classic notion of fairness in computer science. What it means for a predictor to be fair would be that the group membership does not affect calibration. And I'm going to come back to that. That's going to be a thing that we'll close in a little bit. An alternative assumption you could make, which would be different than outcome stability, is what I'm going to call measurement stability. Measurement stability would say that conditional on the outcome of interest and additional covariates, the measurements, the predictors themselves, Ri, are going to be the same across those two samples. So as an example that you could keep in the back of your head, imagine we were trying to infer crop burning from satellite imagery. The underlying crop burning process is what's going to produce the visual signal in satellite imagery. And our idea might be that crop burning looks the same in satellite images, whether that is measured in one part of Malawi or another part of Malawi. And so I'm willing to believe that that process is the same across those two samples. If you were to believe this assumption, in some recent work that I have with Rahul Singh and Davide Viviano, you can work through and still identify quantities of interest in the empirical sample of interest. It's going to look like sort of an IV type problem, conditional moment restriction problem, but I'll punt on all those details for now. And again, I just want to pause and try to interpret what this restriction is actually saying. If we're in a world where the outcome we're trying to measure is binary, and we had some classifier based on satellite imagery, so Ri is also binary, measurement stability would say that the errors of this classifier are going to be conditional on the latent outcome of interest to be the same across those two samples. My predictor should have the same true positive rate and false positive rate in both samples. And again, I'm going to open another bracket. If you went to work on algorithmic fairness, this is another notion of what it might mean for predictors to behave the same across two samples. So what's the relationship between the two of them? Well, if you were to suppose that outcome stability holds, you can go through Bayes' rule, a nice little first-year exercise to ask what is its implication for the measurement channel. And you would see that if outcome stability holds, then measurement stability can only hold if there is a nice cancellation property of the base rates in the outcome and the unstructured data across the two samples. And if you went in the reverse direction and asked, suppose measurement stability hold, what would it imply for outcome stability? Again, outcome stability would only hold if there is nice cancellation in particular terms that depend on the base rates across those two samples. So it would seem like having both of them hold at the same time is a very knife-edge case. I would need some specific properties about how outcomes are varying across these two samples. But differing base rates are exactly what you would expect. The auxiliary sample is often collected somewhere else at some other point in time. A government forest survey run in a different part of Uganda might have a different level of forest cover than the sample you're studying. Mobile phone carrier data from Malawi matched to a particular census year may have different income or consumption patterns than the experiment you're running, say, post-COVID. That's actually an idea you can make very formal and actually show that outcome stability and measurement stability can hold only if the base rates agree across the samples or the base rates differ, but you're in this world where your predictor is perfect. There's no error. Neither of those cases are very reasonable in practice. You would expect base rates to differ across samples if you're doing data combination. The benchmarks we just looked at told you that predictors are imperfect. And while that may seem like a mysterious result at this very fast rate, this is just a restatement of some very classic canonical impossibility results in algorithmic fairness. Basically, the two stability assumptions we wrote down are two different notions of what it means for an algorithm to behave the same across subpopulations. And there's work going back now about a decade ago showing that those two things can't hold in general at the same time. So what's the upshot? These two stability assumptions are very powerful. If you apply them, you can identify the stuff you're interested in, but they're alternatives from one another in general and in practice. So you got to pick and you got to defend the choice. I'm going to go through this part a little quickly. I'll do my sort of, econometrics police work. If you choose the wrong assumption, you're going to get wrong answers. So choose the right assumption, think hard. But if you get the correct assumption right, there's really high returns to this. So let me just illustrate very briefly a semi-synthetic exercise based on this deforestation experiment idea using data from the DRC, Brazil, and Indonesia, where we're going to try to predict forest cover. But we're going to set this up so measurement stability holds, and I want to just illustrate the value of exploiting an assumption when it's correct. The blue line is going to show that if measurement stability holds and you use an estimator that exploits it, you're going to get estimates that are approximately unbiased across a variety of data generating processes. If you use an assumption that does not exploit estimator that does not exploit measurement stability, you can get wildly incorrect estimates. Furthermore, if you exploit the information available in the auxiliary sample correctly, you can really substantially tighten standard errors by taking the assumption seriously and writing down an estimator that exploits it. So the consequences of getting the assumption wrong are bad, But if you get it right, there's really huge upside here in terms of getting unbiased estimates and meaningful improvements in standard errors on the order of 20% relative to some alternatives and even 40% relative to some alternatives. So you can do this in many other empirical settings. I'll refer you to this paper with Rahul Singh and Davide Viviano, where we do this in 2 empirical illustrations. But really, that's focusing on measurement stability. There are large returns in general to exploiting the right stability assumption and doing data combination with ML and AI-generated measurements. So how should researchers choose? We're getting close to, actually we're at over 6 p.m., so I will punt on that and say there's been a lot of work over the last year to try to give people guidance. It's in the slides, it's in the papers. Reach out if you have any questions. And let me just sort of try to wrap up here on what we tried to accomplish across these lectures. For me, AI and machine learning are really accelerating the process, the discovery process across the sciences. I think it's a foundational and important question that we must wrestle with. What would this look like in economics? Our goal in this lecture was to try to provide one answer to that question, which is that machine learning and AI allow us to tackle a measurement problem that we've always faced. The first part is that we collect limited structured measurements from the settings we study, and the second is in settings we study, collecting high quality measurements is very costly, and both of these limit the questions that we can study at scale. And what we tried to argue for you is that there are real opportunities for ML and AI to tackle both of those problems. So the first problem, we collect limited structured measurements. AI provides us with the opportunity to expand the aperture. We are building ML and AI tools to do hypothesis generation from unstructured data. That can give us new ideas to wrestle with using our standard empirical toolkit. And the second problem is that measurement is fundamentally costly in the social sciences, but we can use ML and AI to scale the measurements that we have and we would already defend. And there's really good work thinking about this problem where you have access to a random validation sample, and we're starting to see work in the space where there is no random validation sample and we have to deal with data combination. My last slide that I do in my class, I'll do it for you guys, is I think over the last 25 years, sort of the crowning achievement of statistics and econometrics has been the causal inference revolution. It gave us new ways of analyzing data that unlocked new ways to see the world and opened new questions that we couldn't study before. And I think we are now building the same sorts of toolkits to use machine learning and AI as tools for measurement. And measuring better allows us to see the world in new ways and open up new questions that we couldn't study before. So I hope that, we as a field take up this challenge. I hope that you go out and measure interesting stuff. And please, if you have any questions, I'll offer my own inbox. Please reach out. Love to chat more.